Every second, the world produces 28 million tons of stainless steel. And behind the shine of every spoon, every faucet, every surgical instrument stands one metal: chromium. But here's what's mind-blowing. Chromium melts at 3,375 degrees Fahrenheit, and in the electric arc furnaces that produce it, temperatures hit 5,000 degrees, hotter than the surface of the sun. A single furnace consumes 4,000 kilowatt-hours of electricity per ton of alloy. That's as much as the average apartment uses in 4 months. 80% of all chromium in the world goes into making stainless steel. But where does this metal come from? Why are 99% of the world's chromite reserves concentrated in just a handful of countries? And what happens in that hellish zone beneath the electrodes, where ore transforms into molten ferrochrome? Stick around. You'll discover how black rock gives birth to the metal that makes steel immortal. Picture a massive electric arc furnace as tall as a 3-story building. 3 carbon electrodes up to 6 feet across plunge into a churning mass of glowing ore, coke, and fluxes. Between the electrode tips and the furnace floor, electric arcs crack and snap. Temperatures in this zone hit 5,000 degrees Fahrenheit. That's hotter than the surface of the sun. The air above the furnace shimmers with heat. Clouds of smoke and gas blast out from beneath the half-closed roof. Inside, real alchemy unfolds. Chromium ore mixed with coke melts down, oxygen escapes as carbon monoxide, and molten ferrochrome, an alloy of chromium and iron, flows to the bottom. This is a submerged arc furnace, and this is where most of the world's ferrochrome is born. The process runs non-stop. Fresh batches of ore and coke pour in from the top, molten metal and slag tap out from the bottom. A single furnace like this can pack 25 to 45 megavolt amperes of power. This is a monstrous amount of energy. An entire power plant runs just to melt the ore. When enough molten ferrochrome accumulates in the furnace, workers punch open the tap hole, a special opening in the furnace's side. And then the mesmerizing spectacle begins. A stream of white-hot metal and slag bursts out, flowing down a channel into an enormous ladle. The stream's temperature around 3,000 degrees Fahrenheit. The metal glows bright orange, almost white. The heat radiating from it is so intense that workers stand dozens of yards away, protected by special screens and fireproof clothing. Slag floats to the top and is drained off separately. The ferrochrome cools in massive molds, transforming into solid ingots weighing hundreds of pounds. These ingots are later crushed into pieces of the right size for sale to steel mills. But the process of obtaining ferrochrome, that's only the middle of the journey. It all begins with ore, mined deep in the earth. Chromite, the only industrial ore of chromium. It's a dark brown, almost black mineral with a metallic luster. The chemical formula? Iron and chromium oxide. Pure chromite contains 68% chromium oxide and 32% iron oxide. But in nature, perfect ores like that barely exist. Real deposits contain anywhere from 40 to 50% chromium oxide. Chromite forms in igneous rocks, in massive molten masses rising up from the Earth's mantle. The largest deposits are found in South Africa, Kazakhstan, India, and Turkey. These 4 countries account for roughly 80% of global production. South Africa is the absolute leader. Its deposits in the Bushveld complex contain 200 million tons of chromite. We're talking ore seams stretching for hundreds of miles and plunging thousands of feet deep. Kazakhstan holds reserves of 230 million tons. India? 54 million tons. Now, the story. French chemist Louis-Nicolas Vauquelin discovered chromium in 1797. He isolated it from croquat, a bright red lead chromate mineral. The mineral's vivid color inspired Vauquelin to name the metal after the Greek word chromos, color. Because chromium compounds produce stunning colors: greens, yellows, oranges, reds. A year later, in 1798, Vauquelin isolated pure chromium by reducing the oxide with carbon. Iron with added chromium was first produced in the mid-1800s, and the first use of chromium as an alloying element in steel production happened in France in the 1860s. The revolution came in 1893 when Henri Moisson smelted chromium ore with carbon in an electric furnace and produced ferrochrome. This became the foundation of the modern industrial method, which has evolved but at its core remained the same. Chromite gets mined both through open-pit operations and underground mines. Open-pit mining gets used when the ore sits close to the surface. Giant excavators strip away the soil and overburden, exposing the chromite layers. Then they blast the ore, load it into haul trucks with capacities up to 300 tons, and transport it to the processing plant. Underground mining gets deployed for deep deposits. Tunnels get driven hundreds of feet down, sometimes miles. They blast the ore, load it into mine cars, and haul it to the surface. The extracted ore? It's not pure chromite yet. It comes mixed with waste rock and other minerals. That's why the ore needs processing. First, they crush it in massive jaw crushers. Chunks the size of a car get reduced to fist-sized pieces. Then they grind it in ball mills down to the size of sand or even dust. After that comes separation, isolating the chromite from the waste rock. The main method for enriching chromite is gravity separation. Chromite is heavier than waste rock. Its density is 4.5 to 4.8 grams per cubic centimeter, while the rock is 2 to 3 grams. The crushed ore is mixed with water, creating a slurry. The slurry passes through jig machines, concentrating tables, spiral classifiers, centrifugal separators. Under the force of gravity, the heavier chromite grains settle faster, while the lighter waste rock is carried away by the water flow. Magnetic separation is also used. Chromite is weakly magnetic, but modern high-intensity magnetic separators can attract it and separate it from non-magnetic impurities. After enrichment, they obtain chromite concentrate containing 46% or more chromium oxide. This is ready-made raw material for metallurgy. The concentrate is dewatered, dried, and sent to ferroalloy plants. Lump ore is needed for ferrochrome production. Fine powder doesn't melt well in the furnace. So the fine particles get agglomerated, sintered into large chunks. They mix the concentrate with fluxes and coke breeze, moisten it, and form pellets. Then they heat it to about 2,200 degrees Fahrenheit. The pellets sinter into solid lumps a couple inches across. Now the ore is ready for smelting. At the ferroalloy plant, chromite concentrate gets mixed with coke and fluxes in specific proportions. Coke is the carbon source that'll reduce the oxides down to metal. Fluxes, quartzite, dolomite, limestone, are needed to form slag with the right composition and melting point. The charge, the mix of ore, coke, and fluxes, gets loaded into the electric arc furnace from the top through special hoppers. Loading happens continuously or in batches depending on the furnace type. The electrodes, massive carbon cylinders, are submerged in the charge layer. When they switch on the current, an electric arc forms between the electrodes and the material beneath them. Temperature in the arc zone? 5,000 degrees Fahrenheit and higher. That's enough to melt any ore. Inside the furnace, complex chemical reactions take place. Carbon from the coke combines with oxygen from chromium and iron oxides, forming carbon monoxide that rises upward. Chromium and iron are reduced to their metallic state and fused together, forming ferrochrome. Some of the carbon dissolves into the metal, producing high-carbon ferrochrome with a carbon content of 4 to 8%. Typical South African ferrochrome contains 52 to 54% chromium, 6 to 7% carbon, and 2 to 4% silicon. Ores from Zimbabwe with a higher chromium to iron ratio yield a product with 63 to 67% chromium. The molten ferrochrome and slag accumulate in the lower part of the furnace, the hearth. When enough metal has built up, they open the tap hole. Metal and slag flow into a ladle. The slag floats to the top and is poured off or skimmed away. The metal is poured into molds or cooled in special forms. Once solidified, the massive ingots are broken down by hydraulic presses or hammers into pieces of the required size. Ferrochrome production is incredibly energy intensive. A single ton of high-carbon ferrochrome burns through 2,000 to 4,000 kilowatt-hours of electricity. That's why ferrochrome plants get built in countries with cheap power, often right next to hydroelectric dams. Chromium recovery from ore hits about 90% under good conditions. The remaining 10%, it goes into slag. Slag isn't just waste. Metal particles get extracted from it using mineral processing methods, and what's left goes into construction. Ferrochrome isn't the end product. It gets shipped to steel mills where it's added to molten steel for alloying. Chromium gives steel corrosion resistance, hardness, heat resistance. Stainless steel contains 10 to 20% chromium. Average, 18%. It's chromium that forms a thin, invisible oxide film on the steel's surface, protecting the metal from rust. And so, having traveled from black rock in the Earth's depths, through quarry explosions, crushing and processing, through the inferno of an electric arc furnace at 5,000 degrees Fahrenheit, ferrochrome is born. An alloy that gives steel eternal life and shine, resistant to time and corrosion.
It's 1,250 feet long, 223 feet wide, and from keel to top deck, it stands 112 feet tall, like a 12-story building. This is a supertanker, the largest moving object ever built by human hands. It displaces 440,000 tons. Its holds can carry 3 million barrels of oil, enough to fill up 2 million cars. It won't fit through the Panama Canal, can't pass through Suez fully loaded, and to dock one, ports have to build dedicated offshore terminals. One of these ships cost $130 million, takes 2 years to build, and today, you're going to see how a steel giant capable of hauling an entire sea of oil across the ocean comes to life. Everything starts with the design. The engineering team works on blueprints for 18 months, around 50,000 separate parts, over 125 miles of welded seams. Hundreds of engineers calculate every ton of metal, every degree of hull curvature. A supertanker's hull isn't one solid structure. It's about 200 massive sections, welded individually, then assembled into a single unit. Each section weighs between 300 and 600 tons. When the design's ready, it goes to steel mills. One tanker needs 45,000 tons of specialized marine-grade steel. That's 6 times more than the Eiffel Tower. Steel arrives as sheets between half an inch and an inch thick. Each sheet runs 40 feet long, 10 feet wide, weighing up to 10 tons. Just hauling the steel takes several thousand rail cars. The finished steel storage yard at the shipyard covers 20 football fields. Tanker steel is special. It's a shipbuilding alloy with reduced carbon content and manganese additives. It withstands impact loads at low temperatures and won't crack during storms in northern seas, where water can hit 28 degrees Fahrenheit. Next up, cutting. Steel sheets enter the gas and plasma cutting shop. Plasma torches slice through metal with precision down to 0.04 inches. Arc temperature? 36,000 degrees Fahrenheit. That's 3 times hotter than the surface of the sun. A single sheet, 1 inch thick, gets cut in 2 minutes. but there are tens of thousands of sheets. The shop runs 24/7, 3 shifts, no days off. From these sheets come the future structural elements: frames, stringers, bulkheads, plating. Every part gets marked, numbered, and sent to the next stage. Then, bending. Massive rollers and presses give the steel sheets their required curves: bow plating, rounded sides, stern contours. A 2,000-ton press bends steel like paper. Bend radius? Up to 12 inches per 3 feet of length. Now comes the most critical phase: assembling the sections. Each section is built on a separate assembly pad inside the facility. Think of them as mini factories within this massive plant. Workers lay hull plates onto the jig matrix. Steel frames, the ship's ribs, get welded on. Spacing between frames? Exactly 29.5 inches. Not more, not less. Off by half an inch, and the hull could crack in a storm. Welding is automated and semi-automated. Up to 40 welders work on a single section simultaneously. Weld depth runs 0.3 to 0.4 inches. Every seam gets checked. X-ray, ultrasound, and dye-penetrant testing. One section takes 3 weeks to complete. During that time, they lay down 5 tons of weld metal. After assembly, an 800-ton gantry crane hoists the section and transfers it to the slipway. Before mounting on the slipway, each section undergoes geometric inspection. Laser systems measure it at thousands of points. If even 1 point deviates from the blueprint by more than 1/8 of an inch, the section goes back for rework. Because if one section's crooked, the next 20 won't fit into place. The slipway is a massive dry dock, 1,476 feet long, 295 feet wide, 49 feet deep. This is where the entire hull comes together. Assembly starts with the keel, the central longitudinal beam running the full length of the ship. It's the tanker's backbone. Everything depends on how precisely it's positioned. The keel is aligned using laser levels with accuracy down to 0.08 inches, over 1,312 feet. Then the first bottom section gets mounted onto the keel. Cranes fly it in overhead. 4 riggers guide the 500-ton mass into position with inch-perfect precision. Sections are joined by welding. Each seam runs dozens of feet. Welders work inside compartments, outside on scaffolding, overhead on suspended platforms, sometimes 200 people simultaneously on a single hull. If you're fascinated by how humanity builds machines that challenge the ocean itself, subscribe to the channel. There are many more processes ahead that'll blow your mind with their scale. While the hull is being assembled, the engine room is installed simultaneously. This is the heart of the supertanker. The main engine is a diesel standing 46 feet tall, 89 feet long, weighing 2,300 tons. It's the largest reciprocating engine in the world. Each cylinder is 38 inches in diameter. The piston stroke, over 8 feet. 14 cylinders total. The engine produces 108,000 horsepower, enough to power a city of 50,000 people. It runs on heavy fuel oil and burns through 250 tons of fuel per day at full throttle. It's installed through the upper deck while it's still open. A crane lowers the engine into the engine room in sections. Then specialists assemble it on site. Assembly and calibration of a single engine take 4 months. While assembly continues, installation of the cargo tanks begins. Inside the tanker's hull, up to 15 separate compartments. Each one can store up to 25,000 tons of oil. The tank walls get coated with special epoxy paint in 3 layers. Total surface area painted, over 6.5 million square feet. If you laid out that surface, you get an area the size of 100 football fields. The paint protects the steel from corrosion. Salt, oil, and seawater, a mix that can eat through unprotected metal in a year. And a tanker needs to last 25 to 30 years. Between the tanks run pipelines. The main lines measure up to 35 inches in diameter. Total length of pipe inside the tanker, more than 25 miles. Through them, oil gets pumped in and out at rates up to 17,000 tons per hour. The tanker's cargo pumps, a separate engineering system. Each pump is driven by a steam turbine producing 2,500 kilowatts. There are usually 3 of these pumps. In a single day, they can completely unload a 1,300-foot tanker. Just 15 years ago, that would have taken 3 days. The hull is almost complete. Now they're installing the superstructure, the living quarters and captain's bridge at the aft section. The superstructure stands 92 feet tall, 8 decks. This is where 25 to 30 crew members will live and work during 3-month voyages across the oceans. They paint the hull last. Exterior paint area, 700,000 square feet. 3 coats of primer, 2 coats of top coat. Painting alone takes 2 months. Robotic sprayers work around the clock. The tanker's bottom gets a special anti-fouling paint. Without it, algae and mollusks will coat the hull in 6 months, and fuel consumption jumps by a third. This paint runs up to $20,000 per ton. Once the hull is painted, launch day arrives. They flood the dry dock. Water fills it in 6 to 8 hours, gradually lifting the 200,000-ton beast. The tanker slowly floats up. Tugboats carefully guide it out of the dock. But that's not the end. The next 4 months are spent at the dockside. They install navigation equipment, radar systems, satellite communications, anchor winches. Each winch is the size of a truck. A single anchor weighs 30 tons. Then come sea trials. The tanker heads into open water. They push her to a max speed of 16 knots. They test the steering, the engine, fire suppression systems, emergency bilge pumping. Trials last 2 weeks. Only after every check does the ship transfer to her owner. The maiden voyage of a giant like this is always an event. From the Persian Gulf to Europe, around the Cape of Good Hope, 45 days at sea. In her holds, crude oil worth $300 million. Out in the ocean, she can handle waves 65 feet high. And on the horizon, the next voyage, the next ocean, the next decades of service. Humanity has learned to build ships the size of skyscrapers that carry across the planet what powers our entire civilization. And every one of these tankers is floating proof of what engineering can achieve. Subscribe to the channel.
In the scorched Arizona desert, among endless sands, lies the most expensive graveyard on the planet. 4,000 aircraft, worth over $35 billion. This isn't a museum and it's not a junkyard. This is where war machines that once ruled the skies come to die. Picture this: an area bigger than 2,000 football fields, and on every square foot, stories of wars, victories, and defeats. Legendary B-52s that bombed Vietnam rest here. F-14S that defended the skies over Iraq stand here. New patients arrive every single day. But what happens to these giants after they touch down for the last time? Some get stripped for parts in a matter of weeks. Others sleep here for decades, waiting for resurrection. And some just get wiped off the face of the earth. Stick around till the end. You'll find out how machines worth millions die and why this place is called America's Boneyard. 1946. World War II had just ended, and America faced a problem nobody had thought about. Tens of thousands of warplanes were suddenly obsolete. B-17Es, B-24Es, fighters, bombers, all worth billions. But the world wasn't at war anymore. Selling them was out of the question. The technology was classified. Keeping them on active bases? Too expensive. So the military found a solution. Davis-Monthan Air Force Base in Arizona, a place where it rains 4 times a year, where humidity is practically zero, and where the temperature kills any corrosion. Hard-packed alkaline soil, natural concrete, no need for hangars or runways. The desert climate turned this place into the perfect graveyard for aircraft. The first 600 planes from the war flew in. They were parked in neat rows, mothballed and forgotten. Nobody imagined that 70 years later, there'd be over 4,000 aircraft sitting here. The 60s, the Cold War is at its peak. America is building bombers capable of delivering nuclear weapons to Moscow. The B-52 Stratofortress. Weight, 83 tons. Wingspan, 184 feet. A machine built to destroy cities. By the 70s, they'd built over 700 of them. But technology changes fast. Missiles appear that fly faster and more accurately. Bombers become obsolete. Where do you put these giants? Davis-Monthan. The base is expanding. Now it's not just a storage yard, it's a whole industry. 365 personnel. Mechanics, engineers, preservation specialists. They take in aircraft, assess their condition, and decide the fate of each plane. Some get preserved for long-term storage. Others get stripped for parts within a month. Still others head to the guillotine, a giant machine that slices the fuselage into pieces. The decision comes down to one thing. Does the military need this model? The 90s. The Cold War is over, and at the airplane graveyard, the largest destruction in aviation history begins. The Strategic Arms Reduction Treaty demands proof. Bombers must be destroyed so Russian satellites can see it from orbit. They position a B-52 on the pad, and a 13-ton guillotine drops onto the fuselage. The crunch of metal echoes for half a mile. In 15 minutes, a machine that cost $100 million becomes chunks of aluminum. Cameras capture everything for the satellites, proof of destruction. Over several years, they cut up 365 B-52s this way. Each aircraft is a story. Vietnam, Operation Desert Storm, dozens of combat missions. But treaties matter more than history. The metal goes to the smelter. One bomber yields about 50 tons of aluminum, enough to make 1,200 bicycles. That's how legends of the sky die. The process begins long before the aircraft touches down in Arizona. The military makes the call. This bird is retired. Could be a lot of reasons. Outdated model, maintenance costs through the roof, political decisions, structural wear after thousands of flight hours. The plane makes its final flight. Pilots joke it's the last ride to paradise. Though for the machine, it's more like a waiting hell. Davis-Monthan Base greets it in the receiving area. First thing, complete inspection. Engineers check every system. Engines, avionics, hydraulics, electronics. A detailed report gets compiled. This will determine the aircraft's fate. Category 1. Storage with restoration potential. These birds can return to service in 5, 10, even 15 years. Category 2, an organ donor. Everything valuable gets stripped out. Category 3, my complete disposal. This plane goes under the cutting torch within weeks. Decision made. Preservation begins. If a plane ends up in storage, it's prepped for a long sleep in the desert. This isn't just park it and forget it. It's a meticulous process refined over decades. First, they drain all fluids. Fuel, hydraulics, oils, every last drop. Even the slightest residue can cause corrosion or fire. Then they preserve the engines. They're coated with a special compound that protects the metal from oxidation. The cockpit is sealed. Every opening, air intakes, nozzles, hatches, gets covered with special film. It reflects sunlight and keeps the internal temperature from reaching critical levels. Without it, the cockpit turns into an oven. Desert temperatures in summer hit 120 degrees Fahrenheit. Electronics are sealed in protective bags with silica gel, which absorbs moisture. Landing gear gets treated with anti-corrosion coating. The whole process takes about 3 weeks. After that, the plane is rolled out to its spot. Neat rows like a parade of frozen giants. Here it can sit for years. But most aircraft meet a different fate. They become donors. Picture this. Hundreds of planes flying overhead that need parts. An engine for an F-16 costs $3 million. Brand new. But what if you pull it from a mothballed airframe? $800,000. The savings are massive. That's why there's an entire disassembly industry here. Mechanics show up with orders. Need a radar? Pull it from tail number 412. Need a turbine? That F-15 over there will give up its own. The process is surgical. Aircraft aren't stripped barbarically. They're disassembled by the book. Every part gets cleaned, inspected, tested. They document serial numbers, flight hours, condition. Then they package it and ship it to warehouses. One retired aircraft can give life to dozens still flying. Every year, more than 20,000 parts ship out from here. The value of those parts? Over $500 million annually. The aircraft boneyard operates like a giant parts store for all of American aviation. But some planes aren't so lucky. Their time is truly up. The model's obsolete and nobody needs their parts. Or treaties demand complete destruction. That's when the final act begins. The aircraft gets rolled onto a special pad. This is where the monster works, the Igor guillotine. 13 tons heavy, tall as a 3-story building. It's a hydraulic cutter that can slice a B-52 fuselage clean in half in 20 seconds. Brutal process, but efficient. The blade drops and metal 3/4 of an inch thick cracks like cardboard. The fuselage splits apart. Then excavators with shears roll in. They cut the wings, rip off the tail, crush the cockpit. In one day, a single crew can turn 5 aircraft into a pile of scrap. Aluminum gets sorted by grade, titanium separate, steel separate. All of it goes to the smelter. One F-14 Tomcat yields about 12 tons of metal, enough to make 40,000 soda cans. Circle of materials. But not every plane stays here forever. Some come back to life. History's seen dozens of cases where an aircraft that slept 10 years in the desert took to the skies again. The most famous example? B-1 Lancers. In 2004, they were pulled from service and mothballed. 5 years later, the military realized they'd made a mistake. These machines were still needed. 18 airframes were brought back online. The restoration process took months. Engineers stripped protective coatings, checked every system, replaced all fluids, tested engines. Cost of restoration? $15 million per airframe? That's 10 times cheaper than building new. These B-1s flew combat missions again. Afghanistan, Syria, Iraq. Machines considered dead were dealing death once more. The Arizona desert proved to be better storage than any hangar. Dry air preserved the metal perfectly. Not a speck of rust after 10 years under open sky. "4,200 aircraft sit at the boneyard today. That's more than all the aviation museums in the world combined. This collection's worth over $35 billion. Around 300 new birds arrive every year, and roughly the same number leave. Some for parts, some for the smelter, some return to active duty. The base operates year-round, 365 days. No days off. A staff of 400 keeps this giant machinery of death and resurrection running. The economic impact is massive. Annual savings for the U.S. Air Force, over $1 billion. Money they don't have to spend on new parts. Foreign militaries come here like it's a marketplace. They buy whole aircraft for their museums or training. Australia bought 20 retired F-18 Hornets. Israel took several dozen helicopters. The boneyards become an international hub for trading aviation history. And so, beneath the scorching Arizona sun, ends the life of machines that once embodied power and technology. Each of these aircraft isn't just metal and electronics. These are the stories of pilots who trusted them with their lives. These are missions flown over Vietnam, Iraq, Afghanistan. These are technologies humanity spent decades developing and billions of dollars perfecting. There's no museum romance here. Here's the harsh truth. Every machine is mortal, even those that ruled the sky. But there's a certain justice in this. Aircraft don't rot in junkyards. They donate their organs to brothers still flying. They transform into materials for new technologies. Some resurrect for final combat missions. The aircraft boneyard isn't the end, it's transformation. From the ashes of old machines, new ones are born. And every time a fighter climbs into the sky with an engine stripped from a mothballed bird, somewhere in the desert a metal giant smirks. I'm still flying, just differently.
Every single day, the United States alone extracts over 9 million barrels of oil. A single barrel holds nearly 159 liters. Now multiply that by thousands of wells across the planet. But have you ever stopped to consider what oil actually is and how it is formed? This isn't just a black liquid. It is the result of immense geological forces acting over millions of years deep within the Earth. Oil is born from the remains of ancient life, transformed by pressure and heat into a liquid hydrocarbon. And from there, the modern story begins. A high-stakes hunt, deep earth drilling, and the incredible process that turns this primordial substance into the fuel that moves our world. It's expected that the average daily oil output in the U.S. will soon reach 9.9 million barrels. But what exactly is this substance we call oil? The process of its formation is a slow, powerful saga that unfolds over geological time. It begins with the accumulation of organic material, the remains of ancient plants and animals at the bottom of seas and lakes. Over millions of years, these remains are buried under layers of sediment. Under the immense pressure and heat, this organic matter transforms into a waxy substance called kerogen. Further heating, in a temperature window between 60 and 150 degrees Celsius, triggers the thermal breakdown of kerogen, creating liquid hydrocarbons. And that is what oil is, the distilled essence of ancient life. Once formed, this oil migrates through porous rock until it reaches a geological trap, a structure that blocks its path. Here, it accumulates, forming a reservoir. To find these hidden reservoirs, we must first understand the earth beneath our feet. This is the world of geological surveying, one of the most complex and expensive stages of the process. Scientists use satellite imagery, magnetometers, and seismic waves. Seismic surveying is particularly spectacular. Controlled underground explosions are triggered to send shock waves deep into the earth. By reading the echoes, geologists can map the subterranean landscape and identify potential traps. When a promising zone is identified, the drilling begins. A land or offshore rig becomes a giant mechanical creature operating day and night without pause. The drill string, steel pipes with a cutting bit at the end, bites into the earth, rotating at up to 200 revolutions per minute. A special drilling fluid is pumped down to lubricate the bit and carry rock cuttings back to the surface. A modern well can reach depths of 3 to 5 kilometers, and in some cases 10 or even 12. In Texas or Saudi Arabia, wells are drilled over 8 kilometers long, often with a significant horizontal section to maximize contact with the reservoir. A single drilling operation can cost tens of millions of dollars with no guarantee of success. But when a well strikes oil, it begins its journey to the surface, either under its own pressure or with the help of powerful pumps. Saudi Arabia is one of the world's oil titans. In February, the kingdom was producing nearly 9 million barrels per day, and its position is only set to strengthen, as Saudi Aramco has recently discovered 14 new oil and gas fields. Once the well is completed, the extraction phase begins. In a rich reservoir, the natural pressure is enough to force the oil to the surface. This is known as a gusher, and while it looks impressive, it's now considered an outdated and dangerous method. Modern wells are fitted with complex valve systems, known as Christmas trees, that allow for precise control of the flow. The crude oil emerges and is sent to a processing facility where it is separated from natural gas, water, sand, and other impurities. This often happens right at the well site. The separation is a fascinating process. The mixture enters a large sealed vessel where gravity takes over. The lighter gas rises to the top while heavy water and sediment sink to the bottom. Sometimes, water is trapped in the oil as a microscopic emulsion, which is harder to separate. In this case, chemical de-emulsifiers are added to break it down. To maintain pressure in an aging reservoir, secondary recovery methods are used. Water or gas is injected into the formation through other wells to push the remaining oil towards the production well. These techniques can allow up to 60% of a reservoir's oil to be recovered. The average modern well in the U.S. produces between 500 and 1,500 barrels per day. A single barrel is 159 liters. Multiply that across thousands of wells and you begin to grasp the true scale of this global operation. Crude oil itself is a complex cocktail of hundreds of different hydrocarbons. To turn it into petrol, it must undergo a series of technically demanding stages at a refinery. It all starts with fractional distillation. The crude oil is heated to between 350 and 400 degrees Celsius and fed into a tall distillation column. The various components of the oil vaporize and rise to different heights inside the column before they cool, condense, and are drawn off. The petrol fraction is one of the lightest, and it's typically collected at a temperature between 40 and 200 degrees. But this initial distillation only yields about 15 to 20% petrol. To increase the yield, a process called cracking is used. This breaks down long, heavy hydrocarbon molecules into shorter, more valuable ones. The most common method is fluid catalytic cracking, where heavy fractions are heated to nearly 1,000 degrees in the presence of a catalyst. This allows for a much higher yield of petrol from the heavier residues. Hydrocracking, which uses hydrogen under high pressure, is also used. Ultimately, the petrol yield from a single ton of crude oil can be pushed as high as 40 or 50%. The petrol produced so far, however, has a low octane rating. To fix this, it undergoes reforming, a process that restructures the molecules at high temperatures using a platinum catalyst. In the final stage, additives are blended into the petrol to improve its properties: anti-corrosion agents, anti-knock compounds, and detergents. This ensures engine longevity, reduces harmful emissions, and improves efficiency. A single modern refinery can process up to 400,000 barrels of crude oil every single day. The sheer volume is staggering, especially when you consider that the daily petrol consumption in the U.S. alone is around 1.4 billion liters. A river of ancient life, powering the modern world. Imagine a substance that doesn't melt, leaves not a single drop of water, and simply vanishes into thin air. It can freeze anything within seconds, create thick white fog that rolls across the ground, and even stop life itself if handled carelessly. Dry ice isn't just cold, it's a controlled force of nature that humans have learned to harness. Deep beneath the hum of compressors and swirling clouds of white vapor lies a process that seems like magic, where gas transforms into solid matter at -78 degrees. But where does this gas come from on an industrial scale? And why is dry ice production considered a genuine environmental miracle? Watch until the end and you'll see how something so cold can become one of the hottest businesses in the world. Industrial dry ice is nothing other than solid carbon dioxide, which freezes at the extreme temperature of -78.5 degrees Celsius. Put simply, it's the very same carbon dioxide we exhale with every breath, which plants absorb, and which gives fizz to your favorite carbonated drinks. Unlike ordinary ice, which melts into water, dry ice possesses a remarkable property: sublimation. It transitions from solid state directly to gas, bypassing the liquid phase entirely. That's why it's dry. It leaves no puddles behind, simply disappearing into invisible gas. This unique ability to cool instantly and evaporate without trace has made it indispensable across dozens of industries. In medicine, dry ice is a genuine guardian of life. It's used for transporting vaccines, donor organs, and blood, where every second's delay and every extra degree could cost a life. In cryotherapy, it's applied for targeted freezing and removal of warts. In the food industry, it's become a guarantor of freshness. Frozen products, meat, and ice cream are transported in containers filled with this cold wonder. And in the world of entertainment, dry ice is the chief instrument for creating magic. The thick, heavy fog rolling across stages at concerts and theatrical performances, or smoking cocktails in bars, all of this is the work of dry ice, which creates impressive visual effects when it contacts hot water. Dry ice production takes place at cryogenic plants. These facilities occupy enormous industrial areas, comparable to several football pitches. At the center of the site stand gigantic cryogenic tanks, steel towers up to 50 feet high, capable of holding up to 100 tons of liquid carbon dioxide. Inside the workshops, there's a constant hum, powerful compressors and hydraulic presses at work. From the giant tanks, liquefied gas flows through thick, frost-covered pipes into the very heart of production, the pressing installations. These machines are absolute monsters, capable of compressing up to 500 kilograms of dry ice in a single minute. When liquid carbon dioxide under enormous pressure bursts from the nozzle into a chamber at normal atmospheric pressure, rapid expansion occurs. This process, known as the Joule-Thomson effect, causes the gas to cool and freeze instantly, transforming into loose, snow-like dry ice. A cloud of thick white vapor rises above the pressing chambers as powerful hydraulic presses, with force measuring hundreds of tons, compress this snow into dense, heavy briquettes or fine pellets. Conveyor belts move continuously, carrying away the icy blocks. They pass through refrigerated tunnels where temperature is kept below -40 degrees. Automated machines slice large slabs into smaller pieces or transform them into pellets the size of peas. Packaging machines work at lightning speed. Precisely calculated quantities of dry ice are poured into special polystyrene thermal containers, from small 1-kilogram packets to enormous containers holding hundreds of kilograms. Automatic sealers hermetically close the packages to slow the sublimation process. In 1 hour, a single such plant can produce about 5 tons of product. Now imagine the working conditions in this frozen kingdom. In zones where presses and packaging lines operate, temperature stays below -40 degrees. Workers here resemble polar explorers. They're dressed in multi-layered thermal insulation suits, wearing special gloves on their hands, since direct contact with dry ice causes instant and extremely painful burns. On their faces are protective goggles and masks, as high concentrations of carbon dioxide in the air can cause dizziness and suffocation. Because of this, powerful ventilation systems must operate in the premises, constantly refreshing the air and maintaining safe oxygen levels. To avoid hypothermia, workers labor in short shifts, alternating work in cold zones with breaks in warm restrooms. Many processes are maximally automated to reduce human presence in extreme conditions. But even with such protection, work at these plants demands incredible endurance and the strictest adherence to safety procedures. So where do plants obtain carbon dioxide in such colossal quantities? The secret is that they don't produce it specially, they collect it. It's a byproduct of other major industrial processes. The main sources are ammonia and fertilizer plants, breweries where gas forms during fermentation, as well as petroleum refining and cement works. Rather than releasing this carbon dioxide into the atmosphere, it's captured by special installations. The gas then undergoes multi-stage purification from impurities, is dried and compressed under high pressure, transitioning to liquid state. This process is the brightest example of industrial symbiosis and circular economy, where waste from one production becomes valuable raw material for another. But for all its usefulness, dry ice is a substance requiring extreme caution. Its temperature is so low that it can cause serious burns upon contact with skin. But the main danger lies in its sublimation. Whilst evaporating, dry ice displaces oxygen from enclosed spaces. Being in an unventilated room where large quantities of dry ice are evaporating can lead to suffocation. Tragic cases are known where people suffered fatal poisoning using dry ice to create fog and enclosed swimming pools. Therefore, working with it requires strict adherence to safety rules, good ventilation, use of protective gloves and goggles. Now let's glimpse into the future, because dry ice has an incredibly exciting one ahead. Right now, scientists and engineers are developing technologies where dry ice plays a key role. For example, in fire suppression. Unlike water or foam, dry ice doesn't conduct electricity and leaves no traces, making it ideal for extinguishing fires in server rooms, museums, or power stations. Dry ice pellets are sprayed onto fire, instantly cooling it and displacing oxygen. Another direction is cryogenic cleaning or blasting. Tiny dry ice pellets are fired under high pressure at contaminated surfaces. Striking them, they instantly evaporate, and the micro-explosion caused by rapid gas expansion literally blasts off dirt, paint, or rust without damaging the surface itself. But the most fantastic prospect is terraforming planets. Scientists are seriously considering the possibility of using carbon dioxide, which in solid form covers Mars's polar caps, to create an atmosphere. By melting Martian dry ice using nuclear explosions or gigantic mirrors, one could trigger a greenhouse effect that would warm the planet and make it habitable. So this cold, smoking material that we use today for cooling drinks might one day become the key to transforming the red planet into our second home. This proves that even the most ordinary-seeming substances conceal within them boundless potential that humanity has yet to unlock. "68 million tons. That's exactly how much aluminum humanity consumes in just 1 year. This enormous figure stretches from fizzy drink cans and window frames to the wings of gigantic aircraft. But have you ever wondered how we satisfy such enormous demand without depleting Earth's resources? The answer lies in a revolutionary innovation that's transformed the entire industry: aluminum recycling. Each recycling cycle not only saves up to 95% of the energy required to produce new aluminum, but also allows the metal to be reborn within 60 days, each time retaining its original quality. In this video, you'll witness aluminum's extraordinary journey, from discarded waste to gleaming products that return to everyday life. Unlike many other metals that lose quality with each recycling cycle, aluminum can be used infinitely without losing its original properties. This unique characteristic explains why nearly 75% of all aluminum ever produced is still in use. And the United States has transformed this advantage into industrial might. Thanks to advanced collection and smelting systems, recycled aluminum now comprises over 1/3 of the country's annual supply, saving sufficient energy to power millions of households every year. But the benefits aren't merely economic. Aluminum recycling also plays a critically important environmental role. Each ton of recycled aluminum prevents up to 9 tons of carbon dioxide emissions, representing tens of millions of tons of greenhouse gases that don't enter the atmosphere annually. The recycling journey begins with a step that may seem simple, but ultimately determines the efficiency of the entire subsequent process: collecting aluminum scrap. In the United States, the world leader in aluminum recycling, this system operates on an enormous scale. Every year, tens of millions of tons of aluminum are collected from countless sources, creating a constant stream that feeds the industry. What distinguishes aluminum is its inherent economic value already at the collection stage. A discarded aluminum can is worth many times more than a plastic bottle, giving both individuals and businesses a strong incentive to return aluminum to the production cycle. From collection points across the country, convoys of lorries laden with aluminium scrap steadily roll into enormous sorting yards. Each vehicle is weighed, registered, then its container is tilted to discharge the load onto conveyor belts. Beer cans from supermarkets, food trays from residential areas, and industrial aluminium scrap all converge into towering heaps of shimmering metal resembling silver mountains. Right on site, technicians conduct quick preliminary inspections, promptly rejecting any batches contaminated with excessive impurities or hazardous materials. The atmosphere at the yard is always tense. Thousands of tons of aluminium arrive daily, making this facility the genuine front line of the recycling process. At the recycling facility, streams of aluminum scrap are fed onto long, continuously moving conveyor belts. Optical sensors, acting as electronic eyes, scan thousands of fragments per second, identifying aluminum by its characteristic color and light-reflecting ability. Immediately afterwards, powerful magnets remove any ferrous metals, whilst precisely calculated air jets blow aluminum away from plastic, paper, and lighter rubbish. Through several separation layers, the once chaotic waste mixture gradually transforms into more homogeneous streams of aluminum, neatly collected in gleaming silver heaps. From this point onwards, the aluminum stream becomes chemically homogeneous and strictly controlled, ready to transition deeper into the recycling process. After separation, aluminum scrap is fed into a massive shredding system. Conveyor belts constantly drop beer cans, food trays, and industrial scrap onto counter-rotating steel rollers studded with sharp teeth. With intense crushing force, the metal is instantly destroyed, sending sharp metallic clicks echoing throughout the workshop. In just a few revolutions, hundreds of kilograms of aluminium are drawn inside and shredded into small fragments. A vibrating sieve system controls output size, guaranteeing that all shredded aluminium is reduced to uniform size, creating stable, homogeneous raw material for the next stage. Shredded aluminum fragments are fed directly into industrial furnaces, the heart of the entire recycling process. Depending on scrap type and desired end product, the plant may use reverberatory furnaces, rotary furnaces, or electric arc furnaces. Internal temperature is maintained between 660 and 750 degrees, sufficient to melt aluminum without evaporating valuable alloying components. Aluminum is loaded through an upper hatch or inclined chute, then constantly stirred either by mechanical paddles or controlled air injections. Throughout the melting process, thermal sensors and chemical analyzers work continuously, guaranteeing that each batch of molten aluminum meets precise technical specifications. Even after complete melting, aluminum still contains countless hidden impurities invisible to the naked eye. Aluminum oxides, furnace dust, paint residues, and even oils. To eliminate these contaminants, the plant conducts a refining process directly in the furnace. The most common method is fluxing. A special fluxing agent is added to the molten aluminum. Upon reacting, the flux binds with impurities, forming a light, floating slag layer on the surface. This layer is then removed, leaving behind purer, refined metal. In more advanced systems, inert gases such as argon or chlorine are injected under low pressure. These microbubbles permeate the molten mass, capturing excess oxygen and hydrogen and carrying them to the surface. Once molten aluminum reaches the desired purity, it's directed to the casting zone where it begins to take its first clearly defined physical form. This is a crucial transition from liquid to solid, from amorphous metallic mass to structured units that can be measured and transported. Aluminum is poured into molds of steel, graphite, or specialized heat-resistant materials. These may be vertical molds for ingots, horizontal molds for thick slabs, or water-cooled continuous casting systems. Pouring speed, mold temperature, and cooling intensity all are precisely calibrated. If poured too quickly, aluminum may form gas pockets. If the mold is too cold, metal may solidify unevenly. Once aluminum solidifies inside the mold, a hydraulic system carefully pushes out the solid metal. Mechanical clamps grasp the heavy ingot, often weighing dozens of kilograms, lifting it and placing it onto a parallel steel conveyor. The sound of grinding metal echoes throughout the casting shop, whilst the surface of each ingot still glows faintly red from residual heat. One after another, ingots are extracted in rhythm with equipment operation, lining up in neat rows on the moving belt. Sensors quickly scan each piece, checking shape and dimensions. From the casting zone, rows of solid aluminum ingots begin their journey forward, perfectly aligned like metallic bricks, marking completion of a full production cycle. After extraction from molds, aluminum ingots are moved to a preheating furnace to soften them, bringing the metal to ideal condition for rolling. Once the ingot is ready, it passes through a set of counter-rotating steel rollers where enormous pressure flattens and elongates the aluminum block. This process repeats across several rolling mills, with the gap between each pair gradually decreasing. As a result, the ingot, initially several centimeters thick, gradually transforms into a thin, uniform metal sheet. By the final stage, the sheet reaches its target thickness, often to several hundredths of a millimeter, and moves forward as a continuous strip, then is tightly wound into large coils. Amongst countless products made from recycled metal, the aluminum can is the brightest proof of recycling's power, returning to shop shelves in just a few weeks in completely new form. From massive aluminum coils, the can forming process begins with stamping thin sheets into flat circular discs. These discs are fed into a deep drawing press where in one stroke the metal is stretched into a small cup shape. Then the aluminum cup passes through a series of dies, with each stage making the can taller and its walls thinner. Finally, the outer surface is decorated using high-speed rotographer printing, allowing thousands of cans per minute to receive precise labels.
Every year, the world produces billions of square feet of veneer, a petal-thin material hiding the strength and beauty of entire forests. Picture this. From a single log, you can get enough surface area to cover a football field. That's exactly why this industry is worth over $40 billion annually. From one perfect American walnut log, about 3 feet in diameter, you get anywhere from 10,000 to 30,000 square feet of unique surface. One log, almost an entire football field of veneer. Using veneer cuts the need to harvest valuable tree species by 98% compared to making furniture from solid wood. Instead of cutting down 20 trees to make 20 tables, you can harvest one perfect tree and leave the other 19 growing in the forest. But what's behind that number? How does an ordinary tree go through spa treatments, fiery tunnels, and encounters with scalpel-sharp blades to become luxury furniture? Watch closely. At the end, you'll discover a secret almost nobody realizes. Picture a lumber mill that specializes in veneer production. Massive logs of premium hardwoods, oak, ash, maple, walnut, cherry, arrive here by truck. But not every tree makes the cut. These have to be perfectly straight, tall trees with large trunk diameters, and most importantly, free of knots, cracks, and other defects for a significant height. Every knot is a scar that ruins the perfect grain pattern. That's why only the finest specimens are chosen for a veneer. When one of these perfect logs arrives at the mill, it doesn't go straight to the blade. First, it gets the industrial spa treatment. The logs are submerged in enormous pools of hot water or placed in special chambers filled with hot steam. This isn't about cleanliness. This process, lasting anywhere from several hours to several days, at temperatures around 212 degrees Fahrenheit, does two crucial things. It softens the wood, making it more pliable and cooperative for cutting, and it transforms its color, making it richer and more uniform. After the hot bath, the bark gets stripped from the log. A special machine peels away the rough outer shell, revealing clean wood underneath. And now comes the most critical moment before the main show: centering. The log gets locked into the machine, and an operator uses lasers to find its perfect axis of rotation. This is absolutely crucial. Giant pencil in a giant sharpener. The log starts spinning around its axis, and the blade cuts into the spinning wood and starts shaving off a continuous wide ribbon of veneer, just 1/50th to 1/8 of an inch thick. It's like unrolling a paper towel roll. An endless, wet, flexible sheet comes out of the machine, which is then cut into pieces of the right size. This method is highly productive, but it creates a characteristic chaotic pattern that isn't always valued in high-end furniture. The second method, used to obtain the most beautiful decorative veneer, is called slicing. This isn't a sharpener anymore. It's the world's biggest cheese slicer. Here, a log, or part of it cut into beams, is firmly secured to a movable platform. Above it, or to the side, sits a massive, sharp blade. The platform with the wood moves back and forth, or up and down, and with each pass, the blade shaves off a single, perfectly flat sheet of veneer. It's a slower, less productive process, but it's what gives you that refined, linear, or figured grain pattern we value so much in expensive furniture. Depending on exactly how the log was cut before slicing, you can get different types of patterns: radial, tangential, mimicking the look of solid plank. Freshly cut veneer, no matter the method, is called green. It's soaking wet, flexible like damp paper, and tears easily. It needs to dry. The ribbons or sheets of veneer are carefully fed into a long drying chamber. Think of it as a giant tunnel oven where the veneer slowly moves along on rollers or a mesh conveyor. Hot air circulates inside, gently and evenly pulling moisture out. The process is tightly controlled. Dry it too fast and the veneer will crack or buckle. Within minutes, that wet, floppy sheet becomes dry, slightly brittle but stable. After drying, the veneer sheets have ragged edges. They're stacked high and sent under a massive guillotine. A sharp blade slams down and in one stroke slices off the rough bits, creating perfectly straight edges. Now the sheets are ready for the most critical stage, where it's not machines doing the work, it's people with trained eyes. This is sorting. Specialists carefully inspect each sheet, evaluating its color, grain pattern, and any defects, then sort them into bundles by grade. It's meticulous work because this determines the veneer's price and application. But individual veneer sheets are often too narrow for making something like a tabletop, so they need to be joined into one large panel. This process is called stitching or splicing. Two sheets with perfectly straight edges are fed into a special machine. It presses them tightly together, and a specialized mechanism bonds them. This could be a thin zigzag line of adhesive or a glued paper tape. The result? A large, continuous veneer sheet, ready to be applied to a substrate. Now for some history. Using thin layers of wood goes back thousands of years. Ancient Egyptians used veneer to decorate sarcophagi and furniture 3,000 years ago. But modern industrial veneer production only began in the 19th century with the invention of steam engines and precision machinery. The first veneer peeling lathes appeared in the mid-19th century and revolutionized the furniture industry. Instead of sawing valuable wood species into thick boards and losing most of the material to sawdust, manufacturers could now obtain ultra-thin sheets, maximizing every inch of the log. The global veneer market is a massive industry, turning over more than $40 billion a year. The largest producers are China, the US, Germany, Italy, and Indonesia. Veneer isn't just for furniture. It's used in making doors, musical instruments, yacht interiors, luxury car interiors, and premium space finishes. But the most important application is plywood. Yes, ordinary plywood as we know it is multiple layers of veneer glued together with perpendicular grain direction. This exact structure gives plywood its strength and resistance to warping. And now the most impressive number behind veneer, its efficiency rating. Take one massive, perfectly straight log of premium American walnut, several yards long and about 3 feet across. If you just sawed it into boards, you could make, say, one big table and a few chairs. Now here's the kicker. If you slice that same log into veneer just 24 thousandths of an inch thick, you can get anywhere from 10,000 to 30,000 square feet of unique surface. To put that in perspective, that's enough to cover almost an entire football field from a single log. Using veneer cuts the need to harvest precious hardwoods by 98% compared to making solid wood furniture. Meaning instead of cutting down 20 trees to build 20 tables, we can harvest one perfect tree and leave the other 19 growing in the forest. This makes veneer one of the most environmentally responsible ways to use wood. But veneer has another hidden advantage that few people think about. The thing is, the most beautiful, unique wood grain patterns are often found in the most unusual parts of a tree, where the trunk branches out, in burls, in the root section. If you saw a tree like that into boards, these areas often end up as scrap because they're too small or irregularly shaped. But with veneer production, even a small section with a unique pattern can be turned into several square meters of luxurious material. There are entire categories of exclusive veneer made from burls, wood growths with incredibly complex, swirling patterns. One burl the size of a soccer ball can yield enough veneer to finish an entire study, and this veneer can cost thousands of dollars per square meter. There's even a market for archive veneer, material made from trees cut down decades or even centuries ago and stored in warehouses. Some species of wood that are now protected or extinct can only be found in the form of this archive veneer.
Veneer manufacturing technology is constantly evolving. Modern machines are equipped with laser scanning systems that analyze the log structure before cutting and select the optimal angle and method to produce the most beautiful grain pattern. Computer control allows sheets less than half a millimeter thick to be sliced with precision down to hundredths of an inch. New processing methods are being developed that enable veneer to be stained, embossed with textures, and made to imitate rare species. And so, after journeying from a majestic tree in the forest through a hot bath at 200 degrees Fahrenheit, past a knife sharp as a scalpel, and through the fiery tunnel of a dryer, this material emerges, thin as a petal, carrying all the beauty, history, and unique character of the forest, ready to bring a piece of it into our homes. These billions of dollars aren't just money, they're proof that beauty and practicality can walk hand in hand, allowing us to enjoy nature's unique patterns without causing irreparable harm. Every sheet of veneer is a thin slice of a tree's history, one that lived for decades or centuries, and is now ready to serve humanity for centuries more in the form of beautiful furniture.
Picture a chunk of metal weighing 130 tons, the size of a three-story building, spinning at 100 revolutions per minute. This is a supertanker's propeller, the most powerful driving force ever created by humans. Every second, this propeller pushes 200,000 tons of cargo forward. A single sweep of its blade generates the power of 50 cars. But here's the most incredible part. This giant is cast as a single monolith. No welding, no bolts. One solid piece of bronze or steel. How did humanity learn to cast metal structures the size of a house? You'll discover why a propeller like this takes 2 weeks to cool, how it's machined for 3 weeks, and why the tiniest crack could send a ship to the bottom. Watch until the end. The finale reveals the scale of engineering madness that moves the oceans. This is the story of how titans of the seas are born.
The history of the propeller began in the early 19th century. Before that, ships moved either under sail, by oars, or using paddle wheels. Paddle wheels were inefficient. Half the energy was wasted. In 1836, British farmer and inventor Francis Pettit Smith patented the screw propeller. The idea was simple. Rotating blades screw into the water like a corkscrew into a cork, pushing the ship forward. Early propellers were small, 4 to 5 feet in diameter, made from wood or cast iron. But as ships grew larger, so did the propellers. By the early 20th century, steel steamships over 300 feet long appeared. They required propellers 10 to 13 feet in diameter. And with the arrival of supertankers and container ships in the mid-20th century, propeller sizes reached incredible proportions. Modern ocean giants stretching 1,300 feet need propellers 26 to 33 feet in diameter. That's the height of a 3-story building.
The world's largest propeller was built for the Emma Maersk container ship, one of the biggest vessels on the planet. The propeller's diameter? 31.5 feet. Weight, 131 tons. That's 2 tanks combined, or 17 elephants. The propeller has 6 blades, each the size of a car. Total blade surface area, about 750 square feet, like a big apartment. The ship's engine produces 109,000 horsepower. All that power flows through a single propeller. At full speed, the blade tips slice through water at 125 miles per hour. Water pressure on the blades, dozens of tons per square foot. Any crack, any casting flaw, and centrifugal force rips the propeller apart. The ship's dead in the middle of the ocean. That's why manufacturing these propellers is the pinnacle of metallurgy and engineering. The slightest mistake is unacceptable.
Where and how do they make these monsters? The largest propeller manufacturers are in Japan, South Korea, China, Germany, and the Netherlands. The most famous include Japan's Nakashima, Germany's Mecklenburg Metallgas, and the Dutch Works4. They have foundries the size of a football field and cranes that can lift 200 tons. The process starts with design. Engineers calculate blade shapes on supercomputers. Angle of attack, curvature, thickness, everything affects efficiency. The propeller needs to create maximum thrust with minimal cavitation, the formation of water bubbles that destroy metal. The tiniest miscalculation and the propeller becomes inefficient or wears out fast. After the calculations, they create a full-size wooden model of the propeller. Yes, wood, 31 feet in diameter. Master craftsmen carve it for weeks using blueprints and templates, precision down to a millimeter. This wooden model becomes the foundation for creating the casting mold.
They coat the wooden pattern with a special compound and place it in a massive flask, a steel box the size of a room. Around the pattern, they pack in molding sand, sand mixed with binding agents. The mixture gets packed layer by layer. Each layer is compacted through vibration and pressure. The process takes several days. Once the flask is full, they split the mold into 2 halves and carefully remove the wooden pattern. What remains is a cavity shaped like the propeller, a negative. They coat the interior surface of the mold with a refractory compound so the molten metal won't damage the sand. Then they bolt both halves back together. The mold has to withstand the pressure of 130 tons of liquid metal. They install the gating system, channels that'll feed metal into the mold. It's calculated so the fill happens evenly, without air pockets or cold joints. The mold is ready. Now comes the really impressive part, melting the metal. In the foundry, there's a massive induction furnace, a steel crucible holding 40 cubic meters wrapped in electromagnetic coils. They load it with bronze or alloyed steel stock, bars, ingots, scrap. 140 tons of metal. That's with a buffer. Some will stay in the gates and risers. They flip the switch. Powerful electromagnets induce eddy currents in the metal. The metal starts heating from the inside. Temperature climbs to 1600 degrees Celsius. The metal melts, glows orange, then white. The surface churns. The crew skims off slag, oxides and impurities floating to the top. They add alloying elements, manganese, nickel, aluminum, for strength and corrosion resistance. They pull a sample of the melt, analyze the composition. When everything's ready, they start the pour. The furnace tilts with a special mechanism. Molten metal flows into a massive ladle suspended from an overhead crane. The ladle holds 140 tons. This is the most critical operation. The metal has to be uniform in composition and temperature. The crane moves the ladle toward the mold. The metal glows a blinding white, so bright you can't look at it without dark glasses. The temperature around it climbs to 140 degrees, even though the ladle's 30 feet away. Workers in silvery heat-resistant suits control the pour. They open the ladle gate. Molten metal flows into the gating system, first as a thin stream to preheat the channels. Then the flow gets stronger. The metal fills the mold from bottom to top, pushing air out through special ventilation channels. The pouring process takes about an hour. 300,000 pounds of liquid metal transfer from ladle to mold. When the mold is full, they close the ladle gate. The metal surface in the mold forms a crust of oxides. They dust it with a special powder that creates a protective layer. Now the waiting begins. The metal has to cool and solidify. But at this size, that's not quick. 260,000 pounds of bronze or steel cool slowly, very slowly.
"2 weeks, 14 days the mold sits untouched. Inside, crystallization slowly occurs. Molten metal transforms into solid. Temperature drops at a rate of a few degrees per hour. Cooling too fast leads to cracks from uneven shrinkage. Too slow, large metal grains form, reducing strength. Engineers monitor the process with thermocouples, temperature sensors embedded in the mold. After 2 weeks, they break open the mold. A crane lifts the flask, opens it up. The molding sand pours away, revealing the casting. Before their eyes, a giant propeller covered in black scale. Weighs 150 tons, 20 tons more than the finished product. Excess metal has solidified in the gates, risers, and allowances. The propeller moves to a special stand. Machining begins, transforming the rough casting into a perfect ship's propeller. And that's another 3 weeks of work. First, they cut off the sprues and risers, solidified metal feed channels. They use gas torches and heavy-duty bandsaws. The cut-off chunks weigh several tons each. They'll go back to the melt shop too. Then rough machining begins on turning and milling machines. These are giant machines, a bed 20 meters long, a milling head weighing 10 tons. The propeller is clamped on a rotating table. Cutters remove the stock, excess metal left for machining. Chips fly off in spirals as thick as a finger. Tons of metal are removed per shift. They mill the hub, the central part of the propeller that fits onto the shaft. A hole about 3 to 5 feet in diameter has to be perfectly round and concentric, precision tenths of a millimeter. Then they machine the blades. Each blade is milled to a complex profile, leading edge, trailing edge, face, back. The profile changes from root to tip. It's a three-dimensional, doubly curved surface. The machine runs on computer control from a program based on design data.
After roughing comes finishing. Fine-toothed cutters pass over the blade surfaces, removing fractions of a millimeter. The surface becomes smooth. Then polishing. Abrasive wheels buff the blades to a shine. This is critically important. Surface roughness increases water resistance and promotes cavitation. A perfect surface cuts a ship's fuel consumption by percentage points. For a supertanker, that's millions of dollars in savings per year. After machining, the propeller is weighed and balanced. The center of mass must lie exactly on the rotation axis. Otherwise, vibrations will develop during operation, destroying bearings and potentially damaging the ship's hull. Balancing is done by drilling small cavities in specific locations. The final operation, non-destructive testing. The propeller is X-rayed, checked with ultrasound, examined using magnetic particle inspection. They're looking for internal defects, voids, cracks, inclusions. If they find a critical defect, the propeller is scrapped. 287,000 pounds of metal and a month of work go to waste. The cost of such a propeller, $1 to $3 million. And just like that, making the journey from a wooden model through the hellish heat of 1600 degrees and 140 tons of molten metal, through 2 weeks of cooling and 3 weeks of machining on giant lathes, a propeller is born. the heart of a supertanker, the pulse of an ocean giant. A solid piece of metal the size of a house, weighing 130 tons, capable of transmitting 100,000 horsepower. It's a triumph of engineering brilliance and metallurgical mastery. Every time you spot a container ship on the horizon or an oil tanker in port, know this: beneath the water spins a titan, born in fire and honed to perfection. A monolith of bronze or steel, every square inch of which withstands tons of pressure. A propeller that drives forward half the world's trade. 90% of all cargo moves by sea. This is a story about giants created by humans, about how humanity learned to cast metal the size of a house and machine it with precision down to a millimeter. A propeller isn't just a chunk of metal. It's a symbol of man's dominion over the oceans, a symbol of the technology that connected continents. From wooden model to steel reality, a journey spanning 5 weeks and millions of dollars. A journey repeated hundreds of times a year in foundries across the world, so the planet's fleet keeps pushing forward.
1,300,000,000 meters of submarine internet cables have already been laid on the ocean floors. And every year, this length grows. Also, we can send a message, watch a video, or make a call across continents. Over 95% of all intercontinental internet traffic passes through them every day. Stretched through the depths, they cross volcanic ridges, encounter sharks, ships, and even geopolitics. How are these gigantic infrastructures created? Who designs the routes? How are they laid on the seabed at depths of over 26,000 feet? And what happens when a cable is damaged?
For the internet to cross oceans, a cable is needed that can withstand pressure, salt water, marine life, and decades of operation without repair. It all starts with the central core, a copper or aluminum conductor, through which the main signal travels. Large ingots of purified metal are melted and passed through drawing machines, which repeatedly pull the material through narrowing dies, reducing the diameter to a few millimeters. At this stage, a perfectly round cross-section is formed, one that has no microcracks or air pockets. After drawing, the wire undergoes heat treatment. It is heated to a precisely set temperature to relieve internal stress and make it more flexible. Then it is cleaned of oxides, often by a chemical method, or using abrasive rollers.
The output is a shiny, smooth, almost flawless wire. It is checked automatically for diameter, resistance, flexibility, and surface purity. The wire must withstand kilometers of bending and work without failure, even at depths of several thousand feet. Depending on the type of cable, the wire is either used as a single solid conductor or is twisted from several thinner strands, which increases flexibility and protection against breakage. Once the copper or aluminum conductor is ready, it is immediately fed into an extrusion line, a long machine resembling a tunnel. Inside, polyethylene heated to 482 degrees Fahrenheit, which melts into a thick, viscous cream. The conductor moves along a conveyor and enters the extruder head, where the molten polymer precisely and evenly flows around the metal, like a second body. Every millisecond is important here. Too slow, and drips will form. Too fast, the polyethylene won't have time to adhere. Immediately after this, the cable enters a bath of cooling water, where the polyethylene layer quickly solidifies, tightly enveloping the conductor. The entire surface must be smooth, without a single bubble or crack. This is the first line of defense against moisture. After cooling, inspection. Lasers measure the insulation thickness, and cameras check the surface. If anything is even slightly off, the cable is cut and reprocessed. The next stage is the application of a hydrophobic gel, which acts as an invisible protector. This thick, viscous compound fills all the voids inside the cable, envelops the optical fibers, and creates an internal shield against moisture. In a special chamber, the cable passes through a system of nozzles or rotating heads that evenly apply the gel to the central part and in the space between the fiber elements. The gel resembles a transparent lubricant. It doesn't dry out, freeze, or dissolve in water, even at a depth of 26,000 feet under a pressure of hundreds of atmospheres. Its main property is to repel water. If the cable sheath is ever breached, the gel instantly spreads and prevents moisture from penetrating inside, not letting it reach the sensitive fibers. At this stage, it's also important that there isn't too much gel, otherwise it complicates the further laying of layers, and not too little. Then the protection efficiency drops. Computers precisely regulate the dosage, and operators visually check the filling and uniformity. After application, a short cooling and stabilization.
Now the cable is ready to receive its optical heart, the fiber threads that transmit light from one continent to another. These fibers, usually from 4 to 12 of them, are first grouped into modules. Each module is a flexible capsule with several fibers inside, providing additional protection. The modules are very carefully arranged in a spiral around the central conductor. This configuration allows the fibers to bend without tension, especially during winding and laying the cable at sea.
To keep the fibers in place, they are fixed in a bedding of gel that was applied earlier. There is no glue, only a tight fit and a flexible structure. It's important that no fiber crosses another, breaks, or shifts from its place. The work is almost like jewelry making, although it's done on a conveyor. Afterward, a continuity check of each fiber. A laser beam is sent through them. Even a micro crack or a bend will cause a failure, and the fiber won't pass inspection. If everything is fine, the structure moves on to the next stage, additional insulation and reinforcement. First, an additional polymer layer is applied over the optical fiber structure. Often it's high-density polyethylene, or another flexible waterproof material. It protects against mechanical damage, friction, and moisture. This is again done in an extruder, similar to the one where the first insulation layer was applied. The cable passes through molten polymer and immediately enters a cooling bath.
After cooling, the cable enters the steel wire braiding section. Machines evenly lay steel rods or tapes in a spiral around the already insulated core. In shallow water areas, this armor is thicker to protect against anchors, fishing nets, and shark teeth. At depth, the armor is thinner or absent altogether. After reinforcement, another outer polymer sheath may be added, which seals the entire structure. Operators carefully inspect the cable surface, checking for uniform thickness, no abrasions, burrs, cracks, or armor misalignments. Then, automated tests. Lasers scan the thickness. Cameras capture every millimeter. Light pulses are sent through the fibers again. The signal must pass without delays or losses. If a defect is found at this stage, it is cut out and both ends are joined using a special technology, creating a sealed splice joint.
After inspection, the cable enters the marking section. Here, information about the batch, production date, cable type, and its purpose is printed on the outer sheath. Often, every few feet, so it's easy to identify the cable even during laying on the seabed. And finally, winding onto spools. These are giant drums with a diameter of up to 13 or 16 feet, which can hold up to 8,200 feet of cable. Each turn must lie flat, without twists, and with uniform tension. Automatic systems regulate the speed and tension force, and operators monitor each stage. If the cable is intended for installation at sea, the drums are immediately sent to ships, where they are installed on the deck. If not, they're stored in special warehouses with humidity control, because even minor corrosion can be fatal.
Every rock you hold in your hands could be hiding miles of wire. Sounds insane, but it's true. Copper ore, this gray-green boulder, holds millions of tons of metal that powers every city on the planet. Every wire in your home, every cable underground, every power line stretching across continents. It all started with a chunk of dull rock that got blasted, crushed, and melted at 2,200 degrees. Humanity extracts 25 million tons of copper every year. That's the weight of 4,000 Eiffel Towers. Each ton requires blasting 100 tons of rock, drilling hundreds of feet deep into the earth, processing mountains of stone, and all for a metal that makes up less than 1% of the ore's mass. How do you extract red metal from gray rock? Metal that conducts electricity better than anything else on Earth. How do pits nearly a mile deep give birth to wires that light up megacities? Stick around till the end. You'll see how rock becomes the energy of civilization. Chuquicamata, northern Chile. The Atacama Desert, the driest place on Earth. Home to the planet's largest open-pit copper mine. Depth, 3,300 feet. Width, 2.5 miles. Length, 3 miles. A wound in the Earth's crust, visible from space. Excavators the size of a 3-story building gnaw at rock around the clock. Each bucket, 700 cubic feet. In 1 hour, a single excavator tears out 1,000 tons of ore. Bell AZ dump trucks with wheels 13 feet high haul 300 tons per trip. The road out of the pit, a serpentine stretch 12 miles long. Trucks spiral upward for an hour just to reach the surface. Chile produces 6 million tons of copper a year. That's 28% of the global market. Peru delivers 2.5 million tons. China mines 1.5 million but consumes 14 million. The rest it buys. The US produces 1,200,000 tons. Russia, 700,000. Copper is a strategic resource. Without it, no power grids, no communications, no electronics. Countries fight over deposits more quietly than they do over oil, but no less fiercely. Mining starts with explosions. 100-foot-tall drill rigs bore 12-inch diameter holes 65 feet deep. The well pattern is calculated to the inch. Distance between holes, 16 feet. Each one gets packed with ammonium nitrate mixed with diesel fuel. ANFO, the cheapest explosive there is. One charge, 650 pounds. A single bench takes 400 tons of explosives. Detonation controlled by electronic timers. Each hole blows with a 10-millisecond delay. That creates a destruction wave that fractures the rock without throwing it far. The blast lasts 3 seconds. Sound like an earthquake carries 20 miles. The ground heaves. A 1,000-foot column of dust rises from the pit. When the dust settles, you're looking at 2 million tons of fractured rock. Excavators move in. 24 hours to haul it all out before the next blast. The conveyor never stops. Blast, haul, drill new holes. Blast again. The pit grows 65 feet deeper every year. "6,000 years ago, on the island of Cyprus, people found a strange stone. Green, heavy, with a metallic sheen on the break. When they threw it into the fire, the stone melted and a red liquid flowed out. As it cooled, it turned into metal, soft, flexible, shiny. The ancients called it cuprum, after the island of Cyprus. They made knives, axes, jewelry from copper. But the major discovery happened in 1831. Michael Faraday created the first electric generator. Turns out copper conducts electricity better than any affordable metal. 6 times better than iron. 1.5 times better than aluminum. Only silver beats it, but that's way too expensive. Copper became the perfect conductor. In 1879, Thomas Edison built the first power station on Pearl Street in New York. Copper wires stretched through the streets. Cities began to glow at night. The era of electrification had begun. Demand for copper exploded. What was once used for coins and statues became the backbone of energy. Quarries expanded. Mines went miles deep. Humanity started devouring copper by the ton. The 20th century transformed copper into civilization's circulatory system. Every house requires 440 pounds of copper. Wiring, pipes, radiators. One car, 50 pounds of copper in the alternator, starter, wiring. One wind turbine, 9,000 pounds of copper in the generator windings. A Tesla factory for battery production, 22 million pounds of copper annually. A power transmission line across Siberia, 660 million pounds of copper and thousands of miles of wire. By the start of the 21st century, humanity was mining 33 billion pounds a year. By 2020, 55 billion, a 60% increase in 20 years. The reason? Electrification of developing countries. India's building new cities. China's laying high-speed rail. Africa's installing solar panels. Copper's needed everywhere. The problem is, rich ores are running out. Ore used to contain 5% copper. Now, 0.5%. To extract 1 ton of metal, you need to process 200 tons of rock. Pits are getting deeper, processes more complex, cost higher. but demand's growing faster. Ore from the pit heads to the processing plant. This is where chemistry and physics kick in. First step, crushing. Jaw crushers grind refrigerator-sized rocks down to 4-inch chunks. Cone crushers pulverize them to gravel. Ball mills turn gravel into sand. The mill's diameter, 26 feet, length, 40. Inside, steel balls weighing 110 pounds each spin around. They pound the ore, grinding it to powder. After 8 hours of rotation, the ore becomes dust. This dust gets mixed with water, creating slurry. It flows through flotation machines. These are giant tanks with air pumped in from below. Air bubbles get coated with flotation reagents, chemicals that stick to copper particles. Copper floats to the surface in foam. Waste rock settles to the bottom. The process runs through 10 stages. Each stage increases copper concentration. At the input, 0.5%. At the output, 25%. That's concentrate. From 100 tons of ore, you get 2 tons of concentrate. The remaining 98 tons? Waste that gets stored in tailings ponds the size of a lake. The concentrate heads to a copper smelter. Here it's turned into pure metal. First stage, roasting. The concentrate is heated to 1300 degrees Fahrenheit in the presence of oxygen. Sulfur burns off as sulfur dioxide gas. What's left is sinter, a mix of copper and iron oxides. The sinter gets loaded into a reverberatory furnace. Temperature, 2200 degrees. Silica flux is added. Iron bonds with the silica and floats up as slag. Copper settles at the bottom as matte, an alloy that's 50% copper. The matte is poured into a converter. Pure oxygen is blasted in under pressure. Remaining iron and sulfur burn away. Temperature climbs to 2370 from the exothermic reaction. After 6 hours of blowing, what's left in the converter is blister copper, 98% pure. But that's not enough for wires. You need electrolysis. Blister copper is cast into anodes 2 inches thick. They're submerged in tanks filled with copper sulfate solution. A current of 2 volts runs through. Copper dissolves off the anodes and deposits onto cathodes. After 3 weeks, the cathodes are coated with a layer of pure copper 4 inches thick. Purity, 99.99%. This is market-grade copper, ready to become wire. And just like that, after a journey from an explosion in a half-mile-deep quarry through crushing, flotation, smelting at temperatures above 1800 degrees Fahrenheit, and electrolysis, gray rock transforms into red metal that carries electricity to every home on the planet. Without copper, there'd be no light in cities. No internet. Every data center runs on copper bus bars. No electric cars. A single Tesla contains 175 pounds of copper. No renewable energy. Solar and wind farms need 3 times more copper than coal plants. Every year, humanity lays down 6 million miles of copper wire. That's the distance from Earth to the Sun and back 7 times. 25 million tons of metal connecting continents into a single electrical grid. Copper is civilization's nervous system. Electrical impulses race through copper veins like thoughts through neurons. Factories operate, hospitals save lives, homes glow in the night. All thanks to metal that was once just green rock in the ground. Every time you flip a light switch, remember, between your finger and that bulb, miles of copper wire born from an explosion in a desert quarry on the other side of the world. It's the magic of turning stone into energy. And this magic won't stop as long as cities shine.
Every year, humanity forges colossal anchor chains capable of withstanding a force of over 1,500 tons, enough to hold back an entire freight train loaded with coal. A single link can weigh more than 500 kilograms and be as thick as a tree trunk. But how is such immense strength born from a simple bar of red-hot steel? What brutal trials must every meter of this steel serpent endure before it is trusted to the depths of the ocean? Stay with us until the end to witness a process of fire, sparks, and true engineering alchemy. It all begins not in the forge, but at a steel mill, where a special alloyed steel is created from ore and scrap. This is no ordinary metal. To produce chains that can handle loads of thousands of tons, you need the highest grade of steel, one capable of resisting not only tension, but also the embrittlement that comes from the extreme cold of Arctic waters. After smelting and chemical analysis, the steel is cast into massive cylindrical billets. These billets, while still hot, are passed through rolling mills that, with incredible force, squeeze and stretch the metal, forming it into long, round steel bars with a diameter that can exceed 200 millimeters. The production hall is a kingdom of fire and metal. The air here is thick with the hum of machinery and the sharp, distinct smell of incandescent steel. It is here that the magic happens, transforming a straight bar into a curved, closed loop. First, the steel bar enters the infernal mouth of an induction furnace. In a matter of minutes, a powerful electromagnetic field heats it to 1200 degrees Celsius, making the metal plastic and malleable. The glowing bar is then immediately fed to a bending press. Hydraulic arms effortlessly bend it into its characteristic U-shape. Now comes the critical moment. While still hot, the U-shaped piece is threaded through the last, already completed link of the growing chain. This is how the links are interconnected. The two ends of the U-shaped piece are then brought together and clamped tightly in the giant copper jaws of a welding machine. The process of flash butt welding begins. An enormous electrical current is passed through the joint. The metal at the point of contact instantly melts, accompanied by a blinding flash and a fountain of sparks. At that exact moment, a hydraulic press with hundreds of tons of force squeezes the molten pans together, fusing them at a molecular level into a single seamless piece. The excess metal, known as flash, is immediately sheared off by special cutters. While the link is still hot from welding, a special stud is fitted into its center. This crosspiece not only gives the link additional rigidity, but, most importantly, prevents it from deforming and tangling during use. After the stud is set, the entire chain, or a section of it, undergoes heat treatment. It is reheated to a precise temperature and then rapidly cooled or quenched in a huge pool of water. This process makes the steel extremely hard, but also brittle. To remove this brittleness, the chain is heated again to a lower temperature and left to cool slowly in the air. This final step is called tempering. Not a single meter of a giant chain leaves the factory without undergoing a series of the most stringent tests. This is the guarantee that it will not fail at a critical moment. First, the entire chain is subjected to a proof load test. It is secured in a special testing machine, a colossal hydraulic bench dozens of meters long. The machine begins to stretch the chain with a force significantly greater than its nominal working load. Inspectors meticulously examine every link for any sign of deformation. But the most dramatic trial is the break test. A test sample of several links is cut from the finished batch. It is placed in the same machine and pulled until it shatters. The deafening crack of rupturing metal is not a sign of failure, but the ultimate confirmation of the entire batch's quality. After the mechanical tests, every single link is inspected with ultrasound to detect any hidden internal flaws. Only after successfully passing all these stages does the chain receive its quality certification. Loaded for transport, it looks like a sleeping steel leviathan ready to begin its silent service in the depths of the ocean. For the highest grade chains, this proof load can exceed 1,000 tons. This means the chain is stretched with a force equivalent to the weight of 3 Boeing 747s. The minimum braking load for such products often exceeds 1,500 tons. Behind every giant link is a world of impressive numbers. A single link of a top-grade anchor chain can be forged from a steel bar over 200 millimeters in diameter. The weight of such a link easily exceeds 500 kilograms, more than a grand piano. However, chains are not measured by the link, but in sections. A standard marine section, or shot, is 27.5 meters long. The complete anchor chain for a supertanker can consist of 12 to 15 of these shots, reaching a total length of over 400 meters. Its total weight can easily exceed 250 tons, comparable to the weight of 2 adult blue whales.
Picture this. Glass that once shattered into deadly shards now saves lives. How did humanity transform a fragile substance into armor for your car? Every year, the world produces over 100 million square meters of automotive glass, enough to cover an entire country. But the real magic happens where molten rock becomes a perfectly smooth surface, in furnaces reaching temperatures over 2,700 degrees Fahrenheit. That's hotter than the surface of molten lava. How did ordinary quartz sand become the foundation of a safety technology we can't imagine modern transportation without? What accidental experiment changed the history of automobiles forever? You'll discover how the first safety glass was created, what secrets hide within its layers, and why modern windshields can withstand the impact of a rock at 60 miles per hour. Watch until the end. The finale reveals how many stages glass goes through to protect your life. The history of automotive glass production is closely tied to the development of the automobile industry, which emerged in the late 19th century. When the first cars began appearing on roads, they weren't equipped with glass at all. The open body design only partially protected passengers, while dust, wind, insects, and other hazards made trips extremely uncomfortable. Later, as cars got faster, the need arose to install protection for drivers and passengers. Windshields started being made from ordinary window glass, which, while providing some protection, had a serious flaw. During accidents, it shattered into large, sharp shards, leading to numerous injuries and deaths. Glass sliced faces, necks, arms of drivers and passengers. This was a real problem demanding an urgent solution. The first revolutionary breakthrough in automotive glass came with the creation of laminated glass, and it happened by accident. In 1903, French chemist Edouard Benedictus accidentally knocked over a flask coated with nitrocellulose. The glass cracked, but stayed intact thanks to a thin plastic layer. This accident inspired the scientists to create multi-layer glass, which later became the foundation for laminated safety glass. By the 1910s, laminated glass started appearing in premium automobiles. Its construction consisted of 2 glass layers with a thin, transparent film sandwiched between them. On impact, the glass wouldn't shatter. Cracks would stay trapped in the film. In the 1920s, laminated glass became widely used in windshield production. Its main advantage? Enhanced safety. Even in serious crashes, fragments wouldn't fly everywhere. They'd stay locked in the polymer layer. The next stage in automotive glass development came in the 30s. when tempered glass manufacturing technology was patented. This material was produced by heating glass to high temperatures followed by rapid cooling. As a result of this process, the glass became stronger, and when it shattered, it broke into small pieces with blunt edges, minimizing injuries. In the mid-20th century, tempered glass began to be used for side and rear car windows. It was cheaper to produce compared to laminated glass and provided a sufficient level of safety for these parts of the vehicle. In the 50s and 60s, automotive glass became even more advanced thanks to technological developments. Important changes occurred: improvements to laminated glass, and the development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and durable. Mass production and automation of manufacturing processes allowed for a reduction in the cost of automotive glass. One of the biggest technological breakthroughs in glassmaking came in 1959 with the invention of the float process. This technology, developed by British company Pilkington, made it possible to manufacture perfectly smooth glass by spreading molten glass across a surface of molten tin. Picture this. Red-hot liquid glass pours onto a mirror-like surface of molten metal and spreads itself out, forming a perfectly flat sheet. Thanks to this method, glass became more uniform, stronger, and accessible for mass production. The float process is still the foundation of automotive glass manufacturing today, ensuring precise dimensions, smooth surfaces, and high quality. In the second half of the 20th century, automotive glass underwent even more changes aimed at improving safety and comfort. In the 60s, heating wires started being installed in rear windows to prevent fogging and freezing. In the 80s, glass with special metallic coatings appeared that reflected sunlight and reduced cabin heating. UV protective glass, thanks to new technologies, began providing nearly complete protection from harmful radiation. Modern automotive glass is divided into several types depending on its purpose and manufacturing technology. The windshield is typically laminated glass consisting of 2 layers of glass with a polymer film sandwiched between them. This design ensures that when damaged, the glass doesn't shatter into sharp fragments. Side and rear glass are most often tempered glass, which breaks into small blunt pieces upon impact, reducing injury risk. Panoramic roofs or other specialty glass types often use laminated or tempered glass with special coatings for ultraviolet radiation protection. The main components of glass are natural materials mixed in specific proportions to achieve the desired properties. Quartz sand is the primary ingredient of glass, providing its transparency. It must be extremely pure with minimal impurities. Soda is added to lower the melting point of glass. Lime improves the mechanical strength and chemical properties of glass. Additional additives are used to adjust color, transparency, resistance to ultraviolet light, and other characteristics. The raw materials are purified, dried, and ground to a uniform consistency. It's critical that impurities that could affect glass quality are eliminated as much as possible. After the raw materials are prepared, they're loaded into specialized furnaces for melting. The melting temperature to form glass reaches around 5,000 degrees Fahrenheit. This is the temperature at which stone transforms into liquid. During the melting process, the raw materials become a uniform, viscous fluid. The glass mixture gets stirred to distribute components evenly. This matters. You want to avoid air bubbles or inconsistencies in the finished product. Glass melting furnaces come equipped with modern temperature control systems and process automation, ensuring top-quality end results. After melting, the glass mass undergoes forming, which in modern production is most often done using the float process. Liquid glass flows out of the furnace and enters a bath of molten tin. Thanks to tin's high density, the glass mass spreads evenly across its surface. Under its own weight, the glass forms a perfectly flat and smooth surface. Gradually lowering the temperature, the glass hardens. By the time it exits the bath, it's ready for processing. The float method allows manufacturers to produce glass sheets with precise geometric parameters and high surface quality. After cooling, the glass sheets are cut according to the dimensions needed for automotive production. Automated cutting machines ensure precision in the process. To prevent cracks and chips, the glass edges are ground down. Each sheet undergoes inspection for defects like microcracks, bubbles, or other damage. To guarantee the strength and safety of automotive glass, it goes through a tempering process. The glass is heated to around 1,112 degrees Fahrenheit. Then the glass surface is rapidly cooled by air jets, while the inner layers cool more slowly. This creates tension that increases impact resistance. When tempered glass breaks, it shatters into small, safe fragments, minimizing the risk of injury. Windshields use laminated glass, a construction of glass and polymer film. Its manufacturing involves several steps. A polymer film is placed between two glass sheets. The construction is put into a vacuum press to eliminate air bubbles. Next, the glass is heated in an autoclave to 284 degrees Fahrenheit under high pressure. This creates a rock-solid bond between the layers. Laminated glass has exceptional impact resistance, and when damaged, it stays held together by the polymer film, keeping drivers and passengers safe. To enhance automotive glass properties, various coatings are applied. Anti-glare coatings reduce reflections from the sun or headlights of other cars. UV protection. Special layers block harmful ultraviolet radiation. Hydrophobic coatings make water sheet right off the glass surface. Heating elements. Thin heating wires can be embedded in the windshield, making it easier to clear ice or fog. To achieve the exact shape needed, special thermoforming equipment is used. The glass is heated to a temperature where it becomes pliable and is formed according to the specified parameters. In the final stage, every piece undergoes rigorous inspection. They check for clarity and defects. The glass is tested for impact resistance and load endurance. Standards compliance, dimensional accuracy, shape, and other parameters are verified. The finished automotive glass is packaged to prevent damage during transport. It's shipped to auto plants or service centers where it's installed in vehicles. And that's how, journeying from quartz sand through the hellish flames of furnaces at 5,000 degrees Fahrenheit, through a bath of molten tin, through tempering and lamination, glass is born, capable of protecting life at 75 miles per hour. This is the story of how an accidentally shattered flask changed the automotive world forever. Automotive glass production is a high-tech process combining physics, chemistry, and engineering. Thanks to modern technology and strict quality control standards, automotive glass delivers safety, comfort, and durability. Every time you get in a car, remember, between you and danger, a thin layer of glass that's passed through dozens of production stages to save your life in that critical moment.
Deep beneath the ground in Ohio sits a machine that holds up America's skies. The Mesta 50 press, a 36,000-ton monster that plunges 10 stories underground. It squeezes metal with 50,000 tons of force. That's the weight of 10 Eiffel Towers at once. Without this machine, the United States would have no F-35 fighter jet, no Boeing 787, and when a crack appeared on the press in 2009, the entire American aviation industry held its breath. Today we'll see how white-hot titanium transforms into fighter jet wings under the blow of a steel fist from the Cold War era, and why this machine, and no other, remains irreplaceable to American defense. If you stood outside the Alcoa plant in Cleveland, Ohio, you wouldn't see anything special. Just an ordinary industrial building, gray brick walls, pipes, trucks. But head underground and you enter a world where real power is born. The Mesta 50 doesn't sit on the ground, it's embedded into it. 100 feet down, 10 stories of concrete and steel. Why so deep? Because when 50,000 tons of force slams into metal, the earth shakes for half a mile in every direction. Without this colossal foundation, the press would punch through the ground like a knife through butter. This machine was built in 1955 at the height of the Cold War, and it's still running, almost 70 years. In that time, generations of aircraft have come and gone, materials have evolved, control systems have advanced, but the press remains, because nobody has built anything more powerful. If you're into stories like this about machines that change the world, subscribe to the channel right now and hit the bell so you don't miss the next one. America and the Soviet Union weren't just racing in space, they were racing for the sky. Whoever builds the best aircraft dominates the air, and the best aircraft need parts that can't be made with conventional methods. Picture a turbine blade from an F-35 fighter jet engine. This component is only about a foot long, but it spins at 10,000 revolutions per minute at temperatures exceeding 2,500 degrees Fahrenheit. No welded seam could handle that. It would fail in seconds. The blade has to be solid, forged from a single piece of titanium or nickel superalloy. That's exactly what the 50,000-ton press is for. It doesn't cut or weld, it crushes, takes a red-hot chunk of titanium and transforms it into the precise shape of a wing or blade in a single strike. Press forging doesn't just shape metal, it changes the metal's very structure. The crystalline grain of titanium gets refined and aligned along the part's contours, making it several times stronger than if you cast or machined the same part from stock. The process starts with prep. A titanium ingot heats up in a specialized furnace to 1760 degrees Fahrenheit. At that temperature, titanium becomes soft as clay, but keeps its incredible strength. The metal glows bright red, almost white. You can't look at it without special glasses. When the temperature hits the sweet spot, a robotic arm pulls out the glowing ingot and moves it to the press in seconds. Time is everything. If the titanium cools even 90 degrees, it becomes too hard, and the press can't deform it. The operator literally has no room for delay. Every move from furnace to press is drilled to perfection. Decades of practice, hundreds of thousands of parts. They lay the ingot into the lower die, a massive steel form that mirrors the shape of the finished part. The dies themselves are made from special tool steel and cost hundreds of thousands of euros each. From above, the upper die drops, 330,000 pounds. And then the strike hits. 50,000 tons of force slams down onto white-hot titanium. To put that in perspective, imagine stacking 150 passenger jets on your desk, all at once. Hydraulic cylinders 8 feet in diameter generate pressure of 50,000 psi. That's 3,500 times atmospheric pressure. Under this monstrous force, titanium behaves strangely. It doesn't break. It doesn't crack. It flows. Metal atoms shift, sliding past one another, filling every microscopic corner of the die. In 3 seconds, a shapeless ingot transforms into a perfect replica of a wing spar or turbine blade. The entire factory shudders from the impact. Workers feel the vibration hundreds of feet away, like a minor earthquake. Operators at the press wear specialized ear protection. The sound of the strike reaches 130 decibels, louder than a jet taking off. The strike itself lasts no more than 3 seconds. But in those 3 seconds, something happens that would take hours of conventional machining, and the result is stronger. But the most amazing thing? The precision. Despite the savage force, the press controls the shape to within half a millimeter. Laser sensors track every movement of the die. Hydraulics adjust pressure thousands of times per second. If something goes wrong, a part worth 300,000 euros turns into scrap metal. Mesta 50 produces parts for all major American aircraft: F-35 and F-22 fighters, Boeing 787, Apache helicopter engines. They all carry parts born under the blow of this press. Every month, more than 2,000 tons of titanium and nickel superalloys pass through it. The plant employs hundreds of specialists: metallurgists, press operators, quality control engineers. Each finished part undergoes rigorous inspection: ultrasonic scanning, X-ray, geometry measurement, accurate to hundredths of a millimeter. Documentation for each part is stored for decades. If a plane crashes, investigators can reconstruct the entire manufacturing history of every component. Only after passing all inspections does a part receive clearance for installation on an aircraft. And then disaster struck. In 2009, during a routine press operation, engineers heard an unusual sound: metal cracking. The press was immediately shut down. Inspection revealed something terrifying. A crack nearly 4 feet long had appeared in the main support beam. For the U.S. aviation industry, this was a real shock. Mesta 50, the only press of this power in the country, without it, F-35 production stopped. Boeing couldn't manufacture parts for the Dreamliner. Military contracts were frozen. Every day of downtime cost millions of dollars. The problem was that a 2,000-ton beam can't just be removed and replaced. It's installed in the structure at a depth of 100 feet, surrounded by dozens of other systems. And building a new press of equal power, that's years of work and billions of dollars. The country had neither. Engineers would have to repair it right there on site, 100 feet down, in cramped conditions with no way to extract the structure. A desperate repair effort began. A specialized team of welders worked around the clock for 4 months. They used cutting-edge technology, electroslag welding in an inert atmosphere. The crack was welded layer by layer, each about 1/8 of an inch thick. After each layer, the metal underwent heat treatment to relieve internal stresses. In total, 760 weld layers were laid down. Meanwhile, a backup beam was being fabricated, just in case the repair failed. It was made at another facility and delivered using America's largest crane, capable of lifting 4,000 tons. In December 2009, Site 50 was operational again. 200 engineers watched the first strike after repair. Everyone held their breath. The press struck. The facility shuddered. The titanium deformed precisely to the die shape, and the crack didn't reappear. 4 months of work, 760 weld layers, thousands of hours of heat treatment. It all held. The American sky was saved. Today, the 50 is still running. It's almost 70 years old now, an incredible age for industrial equipment. Modern presses are more efficient and automated, but none reach this kind of force. 50,000 tons remains an unbeaten record for the entire country. The 50 is more than just a machine. It's a symbol of industrial might and engineering determination. Every plane you see in the sky, every military fighter, every wide-body airliner, its structure contains parts born right here, beneath the Ohio ground, under the strike of this steel fist. Over the decades, an entire ecosystem has formed around the press. Thousands of engineers, metallurgists, operators who pass down from generation to generation the knowledge of how to work with this monster. It's proof that sometimes the best solutions aren't the newest ones, but those proven by decades of reliable work under incredible pressure. Literally. Today we're at one of Europe's largest oil extraction plants, where ordinary sunflower seeds become the very same oil sitting in your kitchen. The facility sprawls across dozens of acres, silos towering overhead, pipelines everywhere, tanks as far as you can see. And hanging over everything, this warm, slightly oily air with a nutty undertone. You'd think it's simple, just squeeze and done. But when you see the scale of this operation, you realize, between a seed from the field and that clear bottle on the store shelf, there's an entire chain of processes where temperatures hit 570 degrees Fahrenheit, pressure reaches hundreds of atmospheres, and raw material flows in at thousands of tons per day. Come on, let me show you how it all works. It all begins in the fall, when one grain truck after another rolls up to the plant from the fields. Each semi brings in 20 to 25 tons of sunflower seeds. At peak season, the plant receives up to 300 trucks a day. That's about 7,000 tons of raw material, every single day. But before a seed gets anywhere near production, it has to pass inspection. The lab at the entrance takes a sample from every truck with a long probe, stabbing into the grain pile at different depths. They check moisture, oil content, debris, and damaged seeds. Moisture can't exceed 7%, or the seeds will start rotting in storage. Good sunflower seeds have an oil content of 45 to 52%, meaning almost half the seed is pure oil. If the parameters check out, the truck heads to unloading. The seeds pour into underground hoppers, where elevators lift them into silos, massive concrete towers up to 130 feet tall, where the raw material is stored under controlled temperature and ventilation. From the silos, seeds move along conveyors into the prep area. First step, cleaning. Seeds pass through separators that remove rocks, twigs, stem fragments, and other junk that hitched a ride from the field. Magnetic traps pull out stray metal bits, bolts, wire scraps, anything that could wreck the equipment. After cleaning comes cracking. Special mills split the hull and free the kernel. Think of it like cracking sunflower seeds with your teeth, except at tens of tons per hour. The hull, that's the shell we spit out when we snack on seeds, here they don't toss it. Hulls get pressed into pellets and burned in the plant's boilers, generating heat and steam for production. The facility basically heats itself with its own waste. The clean kernels get crushed on roller mills. Heavy steel rollers flatten them into thin flakes about 12 thousandths of an inch thick. That's called conditioning. The thinner the flake, the easier it is to extract oil later. Surface area multiplies. The meats get sent to roasters, massive multi-tiered vats where they're heated with steam to 200 to 230 degrees Fahrenheit while constantly stirring. This process is called moist heat treatment. It softens the cell walls and lets the oil flow out more easily. The smell in this room is incredible. Thick, nutty, warm, makes you instantly hungry. From the roasters, the hot meats feed into screw presses, powerful machines that look like giant meat grinders. Inside, a steel auger spins, forcing the mass through a narrowing channel. Pressure builds to 4,400 to 5,000 psi, and the oil literally gets squeezed out of the meats, dripping through slots in the press housing into a catch tray. A hot golden stream pours continuously. It's mesmerizing to watch. This is pressed oil, dark, cloudy, with a strong roasted seed smell. Many people think this is the final product, but actually, the press only extracts about 60 to 65% of the oil. The rest hides in the cake, a dense compressed disc that comes out of the press hot and hard as wood. To grab the remaining oil, the cake gets sent to extraction, and this is where the real chemistry begins. The cake is crushed, flattened again into flakes, and loaded into an extractor, a long horizontal unit that looks like a slowly rotating carousel. Inside, the flakes get washed with a solvent, usually hexane, a volatile liquid that dissolves fats but doesn't mix with water. Hexane flows through the layer of cake, soaking up the oil, and comes out the other end as micella, a blend of solvent and oil. The process takes about an hour, and during that time, hexane pulls out virtually all the remaining oil from the cake. The fat content in the spent meal drops to 1%. Meal is what's left of the seed after the double pressing. It's protein-rich, up to 46%, and goes into livestock feed. Essentially, from a single seed, the plant gets oil for people, protein feed for animals, and fuel from the hulls. Zero waste production at its finest. Now we need to separate the oil and hexane. The micella is heated in distillers to 200 to 220 degrees Fahrenheit. The hexane evaporates, its vapors are captured, condensed, and returned back to the extractor. It runs in a closed loop with almost no losses. Solvent losses per ton of oil, just about 2 pounds. The rest goes back into the cycle. What remains is crude extracted oil, dark with a specific smell and tons of impurities. Phospholipids, waxes, free fatty acids, pigments. You definitely shouldn't drink it yet. Refining begins, a multi-stage purification that transforms this murky dark liquid into the clear oil we're used to. First step, hydration. Hot water is added to the oil, and the phospholipids swell and precipitate out as a sediment, which is separated in a centrifuge. The centrifuge spins up to several thousand revolutions per minute and splits the oil and sediment in seconds. This sediment, lecithin, is a highly valuable product used in the food and pharmaceutical industries. Next up, neutralization. They pump an alkaline solution into the oil that binds up free fatty acids. The result? Soap. Yes, actual soap. A centrifuge spins it out, then they rinse the oil with water to get rid of leftover alkali. After that comes bleaching. The oil gets mixed with bleaching clay that soaks up pigments like a sponge, pulling out the dark color. The clay settles, gets filtered off, and the oil turns pale yellow, almost clear. The final and most delicate step of refining is deodorization. The oil gets heated to 440 to 480 degrees Fahrenheit in a vacuum column at just 2 to 4 millibars of pressure, basically the vacuum of space. They blast live steam through the hot oil, and it carries away every last volatile compound responsible for smell and taste. The whole process takes an hour to an hour and a half. What comes out? Completely neutral oil. No taste, no aroma. That's exactly what we buy at the store with the label refined, deodorized. The finished oil is cooled and passed through polishing filters, ultrafine membranes that remove the last microscopic particles. The result? A crystal clear liquid that won't cloud even when stored in the fridge. From the filters, the oil flows into stainless steel storage tanks holding up to 5,000 cubic meters, where it's kept under a nitrogen atmosphere, so oxygen can't oxidize the product. The bottling line is a spectacle in itself. Machines blow plastic bottles from preforms right there on the factory floor, then immediately fill them with oil, screw on caps, slap on labels, and pack them into boxes. Speed? Up to 12,000 bottles per hour on a single line, and there are several lines. In a day, the plant can bottle over 500,000 bottles. Every batch goes through lab testing: acid number, peroxide number, moisture content, clarity, taste, and smell. If even one parameter falls outside spec, the entire batch gets sent back for re-refining. The scale is staggering. A major European plant processes up to 2 million tons of sunflower seeds per year and produces around 800,000 tons of oil. Europe is one of the world's largest producers of sunflower oil, and a significant chunk of production gets exported to dozens of countries. When you're standing on the factory floor, watching that golden stream of oil continuously pouring into bottles, and outside another grain truck pulls up for unloading, you realize what a massive industry stands behind that simple bottle on your kitchen shelf. From a seed in the field to oil in a bottle, dozens of stages, hundreds of pieces of equipment, and thousands of people making sure every single drop meets the standard. And it all started with an ordinary sunflower that turned its head toward the sun somewhere in a field.
Every year, humanity discards more than 10 million tons of electronic waste. Of this, hundreds of thousands of tons are televisions, packed with precious metals, complex plastics, and even deadly toxic substances. But what happens to them after they leave our homes? Did you know that inside one old, bulky television set lies pure gold, silver, and components that could become the heart of new gadgets? This isn't just recycling. This is a high-tech treasure hunt. Today, we'll show you how the most advanced recycling facilities operate and why this process matters more than you might think. It all starts not at the factory, but in our homes and offices. Old, outdated devices are collected at specialized reception stations. In developed countries, this is a well-oiled system, from dedicated containers in supermarkets to trade-in programs run by major retailers. Modern recycling centers aren't grim rubbish tips, but gleaming high-tech facilities. Their primary goal is to extract all reusable materials as efficiently as possible, while safely neutralizing the toxic components hidden inside. At large-scale operations, television recycling is organized along automated production lines, where most processes are carried out by machines rather than people. The first stage at the facility is the medical examination and sorting. Televisions are separated into three main categories: bulky cathode ray tube monsters from the past, slimmer plasma panels, and modern liquid crystal displays. Each type requires its own entirely unique approach. Then the undressing begins. Robotic manipulators or workers strip away the plastic casings. This plastic is immediately sent to giant shredders where it's ground into tiny fragments which, after remelting, will become parts for new motor cars or casings for other electronics. Metal frames and fixings are also separated and sent to their own recycling line. Once the casing is removed, the defenseless innards of the television move on to the dismantling line. Old cathode ray tube televisions receive particular attention. They can genuinely be described as environmental dirty bombs. The most hazardous component is the cathode ray tube itself. It contains up to several kilograms of lead, which was used to prevent X-ray radiation, whilst the internal surface is coated with a layer of phosphor containing toxic rare earth metals. Consequently, they're dismantled with exceptional care, often by hand, within sealed chambers. First, a specialized heated wire or laser carefully separates the front clean glass from the rear lead-laden funnel. The glass is then cleaned, crushed, and sent for recycling, whilst the lead is extracted for manufacturing new batteries. Modern liquid crystal displays are no less hazardous. Hidden along the edges of the panel, thin as spaghetti, are fluorescent backlight tubes. Each of these tubes contains a small but highly dangerous amount of mercury. That's why LCD panels are dismantled in specially sealed boxes with powerful ventilation systems. Robotic arms or workers in protective suits carefully extract these tubes. They're placed in hermetically sealed containers and sent to specialized facilities where the mercury is safely extracted and purified for reuse. The liquid crystals sandwiched between the glass layers present another challenging component. They're extracted using chemical solvents. Plasma panels require their own approach. Unlike LCD displays, they don't contain mercury, but their cells use inert gases such as xenon and neon. The panels are dismantled, the gases are collected in special containers for reuse, whilst the high-quality glass that makes up the screen is crushed and purified. Once the screens and casings have been neutralized and sent on their separate ways, the most valuable parts remain on the conveyor belt, the circuit boards. This is where the precious metals are hidden. Copper wires, aluminum heat sinks, and other metallic components are separated and sent off for smelting. The most important and complex part is processing the printed circuit boards. It's in these boards, within the microchips and connectors, that you'll find microscopic yet incredibly valuable quantities of gold, silver, palladium, and other precious metals. First, the boards are shredded into fine particles. These particles are then sent to the chemical workshops. The most common extraction method is chemical leaching. The shredded boards are immersed in special acid solutions. To extract gold, they often use aqua regia, a mixture of concentrated hydrochloric and nitric acids, which can dissolve even this noble metal. After the precious metals have dissolved into the solution, the precipitation process begins. Special chemical substances are added to the liquid, which cause the pure metals to fall out as sediment. For instance, ferrous sulfate is used to precipitate gold. This gold sediment is then thoroughly washed, dried, and remelted into small but incredibly valuable ingots. Similar methods are employed to extract copper and silver, though using different, less aggressive acids or the electrolysis method. In the final stage, all the recovered materials, gold, copper, aluminum, glass, and plastic, are compressed into compact blocks. Each year, millions upon millions of televisions are discarded worldwide, with their combined weight running into millions of tons. In Europe alone, for instance, electronic waste exceeds 10 million tons annually, and a substantial portion of that comprises televisions and monitors. This staggering figure isn't merely a statistic, it's testament to our rapid technological advancement and its darker consequences. But there is encouraging news. Year on year, growing numbers of people are recognizing the importance of proper disposal. Hundreds of thousands of tons of old televisions now find their way to recycling facilities each year, helping us preserve our air, water, and finite natural resources. Here's what the real secret we mentioned at the beginning is all about. Your old television isn't rubbish, it's a genuine urban mine. A single ton of old circuit boards contains 40 to 50 times more gold than a ton of gold ore extracted from a traditional mine. Electronics recycling isn't simply about caring for the environment, it's an incredibly profitable business of the future. We've learned to extract the most valuable resources not from beneath the ground, but from what we ourselves have created and discarded.
And every time you take an old television for recycling, you're not just getting rid of clutter. You're returning precious metals to the economy and helping to make our world a bit cleaner.
What if I told you there's a metal that flows like water at room temperature, killed thousands of workers during the colonial era, and without which gold mining would be impossible? A metal that vaporizes at 1100 degrees Fahrenheit and condenses back into liquid silver? Every year, the world produces around 1,300 tons of mercury, but that's nothing compared to historical scales. Over the last 500 years, humanity has extracted about 1 million tons of mercury from the Earth's depths. Half of that million was used before 1925. Mercury is obtained from red ore, cinnabar, by heating it to 900 to 1100 degrees Fahrenheit. During this process, mercury sulfide breaks down, releasing mercury vapors and sulfur dioxide gas. China dominates production, 95% of the world's mercury. In 2022, China produced 2,000 tons of mercury. A standard flask holds 76 pounds of mercury. These were the exact flasks used to ship it to gold mines during the gold rush. Stick around till the end. You'll discover a secret that even those who work with this metal won't talk about. Picture an underground mine somewhere in China, Kyrgyzstan, or Mexico, the world's biggest mercury producers. Deep beneath the surface, in the dim glow of miners' lamps, red streaks appear in the rock. This is cinnabar, mercury sulfide, a bright red mineral that humanity has known for thousands of years. The ancient Romans mined it both as a pigment and for mercury. The ancient Egyptians were using mercury as far back as 1500 BC. Greek philosopher Aristotle in 350 BC described how cinnabar was heated to extract mercury for religious ceremonies. Cinnabar forms in veins associated with volcanic activity and hot springs. About 90% of deposits require underground mining with tunnels. The remaining 10% can be extracted through open-pit methods. Cinnabar is separated from the surrounding rock through drilling and blasting or using powerful machinery. The ore is hauled out of the mine on conveyor belts or in trucks. Because cinnabar is a relatively concentrated ore, it can be processed directly without intermediate steps to remove waste rock. The ore is first crushed in one or more cone crushers. A cone crusher consists of an inner cone rotating on an eccentric vertical axis inside a stationary outer cone. When ore is fed into the top of the crusher, it gets squeezed between the two cones and breaks into smaller pieces. For concentrating low-grade cinnabar with a specific gravity of 8 to 8.2, gravity and flotation methods are used. Grinding to -48 mesh is the economically viable liberation point for the mineral. Some operations use mineral jigs to recover coarse heavy mineral and any metallic mercury that might be present in the ore. Flotation with one or more cleaning stages is used to produce a high-grade concentrate. It's not uncommon to obtain concentrates containing 40 to 50% mercury from ores containing 5 to 15 pounds of metal per ton. The concentration ratio is therefore high. The dewatered concentrate from flotation is combined and stored for roasting and recovery of metallic mercury. Now comes the most critical and dangerous stage, roasting. Cinnabar concentrate gets loaded into specialized furnaces. These can be multi-hearth furnaces, where ore mechanically moves down through a vertical shaft from one level to another via slowly rotating rakes. Or rotary kilns, where ore tumbles along the length of a long rotating cylinder, tilted a few degrees from horizontal. Either way, heat comes from burning natural gas or other fuel at the bottom of the furnace. Heated cinnabar reacts with oxygen in the air at temperatures ranging from 930 to 1,110 degrees Fahrenheit. A chemical reaction occurs. Mercury sulfide breaks down into sulfur dioxide gas and mercury vapor. Mercury rises as vapor. This is called roasting. Mercury vapors rise upward and exit the furnace along with sulfur dioxide, water vapor, and other combustion products. Significant amounts of fine dust from the crushed ore also get carried away and must be separated and captured. Next comes condensation. Hot gases containing mercury vapor pass through a cooling system. A condensation column is used, a special device where the vapors cool down and mercury condenses back into liquid metal. Pure mercury separates from sulfur in this process and evaporates easily. The condensation column collects the liquid metal. Thanks to mercury's high specific gravity, impurities gather on the surface and can be easily removed. The liquid mercury gets poured into standard iron flasks. Each flask holds 76 pounds of mercury. That's the standard unit of sale. These exact flasks shipped mercury to gold mines during the gold rush in California and Nevada in the 18th and 19th centuries. The process is simple in essence, with one drawback: toxic fumes. If roasting is done incorrectly, mercury vapors, which are highly toxic, can get released into the atmosphere. This was catastrophic for workers in the colonial era. The history of mercury production is full of tragedies. In 1564, cinnabar mining began in Huancavelica, Peru. With a local source of mercury, the amalgamation process was adopted for refining silver in Potosi, Bolivia, in the early 1570s. As a result, massive quantities of mercury were released into the environment. Between 1564 and 1810, approximately 17,000 tons of mercury vapor were released into the atmosphere in Huancavelica and 39,000 tons in Potosi. In 1604, an advocate for indigenous people described how fumes, dust, and candle smoke in the mine caused coughing and Huancavelica disease, and argued that forcing people to work in mercury mines meant sending them to a slaughterhouse. In 1630, a contemporary described the mines as a living image of death and a dark shadow of hell. The Jesuit José de Acosta, around 1590, wrote about the roasting process. If the smoke or fumes reach the people opening the pots, they get mercury poisoning and die, or are left in very poor condition or lose their teeth. The largest mercury deposit in history? Almaden in Spain. It was worked from Roman times until 1989, the world's biggest producer. In 2000, Almaden yielded 236 tons of mercury. Other major deposits: Khyber Khan in Kyrgyzstan, 550 tons, Algeria, 240 tons. During World War II, mercury production was critical. Mercury fulminate was essential for bullet primers, and the biggest producing region in Spain was under dictator Franco's control. The U.S. ramped up domestic production from 1941 to 1944. The price per flask during the war years averaged around $380 in 1960 prices. Today, global mercury production has plummeted. In 2016, they produced 4,500 tons, but in 2023, just 1,200 tons. China dominates with 95% of world production, 1,000 tons in 2023. Mercury has diverse applications, but its use is declining due to toxicity. Mercury easily forms amalgams with other metals, making it useful for extracting gold and silver. Much of the incentive to develop mercury deposits in the United States arose after the discovery of gold and silver in California and other western states in 1800. When mercury mixes with gold slurry, it triggers a reaction that separates gold from ore. This amalgam is then heated to vaporize the mercury and leave behind gold nuggets. Artisanal and small-scale gold mining is the largest source of anthropogenic mercury emissions, accounting for 38% of global releases. Other applications include chlorine and caustic soda production in mercury cell electrolysis plants. Until recently, this was a major consumer. In 2023, only one such facility was operating in the U.S. electrical devices, fluorescent and mercury vapor lamps, mercury batteries, switches, and relays. Measuring instruments, thermometers, barometers, pressure gauges. Dental amalgam, a mixture of mercury with silver and other metals for fillings. But because of its high toxicity, mercury use has dropped sharply over the last 20 years. Inhaling mercury vapor is especially dangerous for the kidneys, central nervous system, respiratory and cardiovascular systems. Inhaling mercury vapor also causes neurobehavioral disorders like hand tremors and mental impairment. Exposure to other forms of mercury, particularly methylmercury, which accumulates in fish, can also lead to kidney problems, lung issues, and central nervous system damage, as well as arthritis, reproductive problems, memory loss, psychosis, and in some cases, death. The United States banned the export of elemental mercury on January 1, 2013, under the Mercury Export Ban Act of 2008. Global mercury resources are estimated at around 600,000 tons, mostly in China, Kyrgyzstan, Mexico, Peru, Russia, Slovenia, Spain, and Ukraine. And so, having traveled from red cinnabar ore through roasting at 1100 degrees Fahrenheit, through evaporation and condensation, through the tragedies of thousands of workers in the colonial era, through the gold rush and world wars, emerges a liquid metal that flows at room temperature, without which gold mining would be impossible, but which has killed more people than any other metal in human history. Imagine if construction could be not just strong, but ultra-lightweight, durable, and environmentally friendly all at once. That's exactly the revolution fiberglass rebar brought to the table. A modern material that's gradually replacing classic steel rebar in countries around the world. China produces it especially aggressively, a giant controlling a massive share of the global market. But what is this secret material that's changing the game? Fiberglass rebar is 4 to 5 times lighter than steel, never rusts, withstands harsh environments, and lasts over 50 years. China produces more than 500 million pounds of this stuff annually and controls 60% of global exports. But why are Western countries afraid of this dependency? What role does fiberglass rebar play in Beijing's geopolitical strategy? And how do they make this material that starts as molten glass at 2,700 degrees? Stick around till the end. You'll learn about projects where this material has already changed the future of construction. Fiberglass rebar. These are reinforcing rods made from a composite material based on fiberglass, impregnated with specialized resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and withstands harsh conditions, like acid rain, salt spray, and high humidity. To put it in perspective, standard steel rebar weighs nearly half a kilogram per meter of length, while fiberglass rebar weighs around 120 grams for the same size. This means it's easier to work with, requires lower transportation and installation costs, and as a result, construction becomes faster and cheaper. China holds the leading role in global fiberglass rebar production. Factories located primarily in the eastern and central regions of the country are equipped with modern pultrusion, molding, and fiberglass polymerization lines. Chinese manufacturers produce over 500 million pounds of these materials every year, with exports making up about 60% of total global volume. China's huge advantage isn't just scale, it's price. Thanks to low-cost electricity and resources, Chinese products often undercut competitors from the US and Europe. But this triggers intense geopolitical debates. Zoom out, and fiberglass rebar has become a real hot card in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. Here's the secret angle. China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in Asia, Africa, and Latin America, Beijing is aggressively pushing this material via its global construction corporations operating under the Belt and Road Initiative. This allows China to not only expand its presence in the global construction market, but also strengthen economic influence in these regions through control over building resources. The trend toward fiberglass rebar isn't just about cost savings or new materials, it's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the US, where more and more bridges, roads, and homes are being built using lightweight composites. Unlike metal, this material doesn't corrode, making infrastructure more reliable and longer lasting. According to reports from the American Association of Construction Materials, average construction costs using fiberglass rebar drop by 20%, while structural lifespan doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, less environmental impact, and industry growth. Picture this: you're building a bridge or a high-rise. Instead of heavy steel rebar, you're using thin fiberglass rods. They can be longer, lighter, and easier to install. Plus, you don't have to worry about them rusting years later and causing the concrete to deteriorate. China's already deploying its fiberglass rebar on massive construction projects. In major districts of Beijing, Shanghai, and Guangzhou, new highways and bridge spans are going up with these materials. Around the world, Chinese companies are supplying this rebar to projects in the US, Europe, and the Middle East, strengthening their technological and economic footprint. It all starts with glass, the raw material for making glass fibers. Glass is produced from a mixture of sand, limestone, and soda. These ingredients head into massive industrial furnaces, cranking up the heat to 2,700 degrees Fahrenheit. Here, the mixture melts down into liquid glass. Then, molten glass flows through specialized openings, spinnerets, forming thousands of thin filaments. These fibers get cooled and gathered into bundles. This creates primary fiberglass, thin, flexible, and incredibly strong strands. To give the fibers their necessary properties, they're treated with a special chemical solution, an organic binder, or silane. This coating ensures a rock-solid bond between the fiberglass and the polymer matrix that comes next. The treated filaments get collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main event, forming the composite matrix. The raw material? Polymer resins, typically epoxy, polyester, or vinyl ester. They deliver high-strength performance and provide resistance to moisture and chemical exposure. Bundles of fiberglass are dipped or soaked in a polymer resin solution. The fibers get evenly coated with polymer, and excess resin is removed to prevent clumps and irregularities. The prepared wet bundles feed into a specialized forming line, an extruder. Here, the molten composite is pushed through forming dies, shaping it into rods or bars of the required diameter. Then comes a critical step, pulling and polymerization. The finished reinforcing rods immediately move to cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a unified structure. Dimensional and shape control is crucial, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard diameter for fiberglass rebar ranges from 1/4 inch to about 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During manufacturing, it passes through forming rollers that create ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It grips firmly in the concrete mass and won't slip under load. At the end of the production line, workers or automated systems cut the reinforcing bars to standard lengths, typically 20 feet or 40 feet. The bars are bundled into packages that are easy to transport and store. Each batch goes through testing for strength, flexibility, and corrosion resistance. Manufacturers often guarantee the rebar will last over 50 years, several times longer than traditional steel reinforcement. Fiberglass rebar is gaining more and more importance in modern construction thanks to its lightweight, strength, and corrosion resistance. You're about to see some of the most interesting projects actively using this innovative material. Delhi Metro, Phase 4 in India. A massive metro project where this rebar is being used extensively to reinforce tunnels and structures. This helps extend the lifespan of the infrastructure and reduce the weight of construction materials. Jizan Flood Mitigation Channel in Saudi Arabia, the world's largest project using fiberglass rebar, designed to reinforce long channels for flood control. We're talking 240 tons of fiberglass rebar that need to provide high resistance to aggressive environments. Muskrat Falls Hydroelectric Project in Canada. Rebar manufacturers are supplying material for reinforcement that guarantees the hydroelectric plant's long service life, especially under conditions of water contact and high humidity. The Sunshine Skyway Rest Area Seawall in Florida, USA. A marine structure where fiberglass rebar is the ideal material due to its corrosion resistance in salt water. Here it reduces the need for repairs and extends the service life of the walls. The Alligator River Bridge in North Carolina, USA. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Toronto's TTC North Subway Extension Tunnels in Canada, a project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic events. And just like that, traveling from molten glass at 2,700 degrees through the formation of ultrafine fibers, polymer resin impregnation, and ribbed surface creation, a material is born that serves for over 50 years without a single trace of corrosion. This is a story about how humanity learned to create rebar lighter than air and stronger than steel, a material that's changing the geopolitics of construction and making bridges eternal. The fastener industry is a true empire worth over $90 billion annually. And its flagship products? Massive bolts and nuts that hold our entire industrial infrastructure together. They're not just chunks of steel with machined threads. They're the result of a complete process involving metallurgy, high-pressure forging, heat treatment, and incredibly rigorous mechanical testing. One tiny deviation in material quality, shape, or tightening force can render an entire joint unsafe. In this video, we're going inside the production line that creates giant hex bolts and nuts to show how raw steel transforms into the mechanical foundation of the modern world. The production process for heavy-duty bolts and nuts begins with one fundamental stage: cutting raw blanks. Large diameter steel bars rolled from high-strength alloy steel are fed into industrial cutting machines and divided into segments with precisely controlled length and weight. Modern cutting systems use hydraulic shears or powerful industrial saws, producing clean square cuts that don't distort the metal's internal structure. Throughout the cutting operation, coolant is sprayed directly onto the contact zone to reduce temperature, minimize friction, and wash away metal chips. This maintains cutting tool stability and ensures the blank surfaces remain clean and free from thermal damage. Typically, bolt blanks are roughly twice as long as nut blanks, because bolts require additional material to forge the load-bearing shaft and head in a single production run. During one shift, each cutting machine can process thousands of bolt and nut blanks. Each cut takes just a few seconds, yet the allowable tolerance is extremely tight, because the final shape and mechanical strength of the product depend entirely on the initial dimensions of these blanks. After the blanks are cut, the bolts and nuts move to the heating stage, but the way heat is applied to each component isn't quite the same. For nuts, the entire steel blank feeds into a continuous furnace and is uniformly heated to a temperature range of 1900 to 2100 degrees Fahrenheit. Heating the entire body allows the blank to reach a fully plastic and uniform state. So during forging, the metal can flow evenly inside the die and form a solid hexagonal body before the internal hole is drilled and threads are cut. Temperature is tightly controlled to prevent surface burning while ensuring the core remains soft enough for proper forming. Bolts, however, are heated differently. Instead of heating the entire blank, only the head portion of the steel rod passes through an induction heating system. In a matter of seconds, the front end reaches forging temperature and glows bright orange-red, while the shaft behind it stays significantly cooler. This localized heating method concentrates energy exactly where the hex head needs to form, reduces overall energy consumption, and preserves the mechanical structure of the bolt shaft, which is the primary load-bearing section of the fastener. Right after reaching forging temperature, the blanks are transferred directly into the hot forging zone for shaping. For nuts, the entire evenly heated blank is placed inside a closed forging die, where a high-powered hydraulic press forces the metal to flow according to the die's shape, forming a solid hexagonal body. Under this intense compression, the metal densifies, and its crystalline grains reorganize into a tighter structure, making the steel denser and more uniform. Between each press cycle, the forging die is sprayed with a layer of high-temperature coolant and lubricant. This helps control heat, reduce friction, and protect the die surface during continuous operation. For bolts, the forging process focuses on the head section that was induction heated. The blank is positioned so the hot end sits precisely inside the die, and the press applies force, causing the metal to flow outward, forming the hexagonal head. At the same time, the die is also sprayed with the same type of high-temperature lubricant used in nut forging. When the fluid contacts the hot die, it instantly vaporizes and creates a temporary protective film. This prevents metal adhesion and ensures the bolt head forms cleanly, with sharp, clearly defined edges. Right after forging, both the bolts and nuts are dumped straight into large steel containers for natural cooling in the open air. For big components, this cooling stage typically runs anywhere from 30 to 60 minutes, and can take even longer if the steel mass is particularly heavy. This slow cooling method prevents thermal shock, minimizes the risk of microscopic cracking, and keeps both the shape and the internal structure of the metal stable before the parts move on to the next production stages. Once fully cooled, the bolts and nuts are transferred to the surface cleaning stage. At this point, they're typically loaded in bulk into rotating drum cleaners or vibratory tumbling machines. The rotating drum moves slowly and steadily, creating mechanical friction across the entire surface of the bolts and nuts. This process sharpens the hex edges and leaves the metal surface clean, dry, and uniform. In large-scale production lines, each batch can handle anywhere from a few hundred to several thousand parts at once. Tumbling time usually ranges from a few minutes to several dozen minutes, depending on the size of the parts and the level of oxide scale stuck to their surfaces. Once the surface is cleaned, the bolts and nuts move to the identification marking stage. For nuts, markings are stamped directly onto the hexagonal body, while for bolts, markings are placed on the top face of the head. These symbols indicate the strength grade, technical standards, and manufacturer of each part. They function as an official ID card, mandatory for bolts and nuts to be approved for use in industrial structures, heavy machinery, and large-scale construction projects. Once they've achieved their final shape and received their identification markings, bolts and nuts enter one of the most critical stages of the entire process: thread machining. The threading process for bolts typically begins with a light finishing turn on the shank to achieve a precise diameter and a sufficiently smooth surface. On the lathe, the bolt is firmly clamped and rotated at a steady speed, while the cutting tool simply glides over the surface to correct dimensions before threading. After this, the workpiece is transferred to a thread rolling machine, where 2 or 3 thread rolling dies, engraved with the precise thread profile, press against the shank under high pressure. Thread rolling is a cold forming process that doesn't remove material but rather deforms the surface of the shank, creating threads through plastic flow of the metal. This produces stronger threads with improved fatigue resistance compared to threads cut by a cutting tool. For nuts, threads are created through the tapping method. First, a specialized drill bores a vertical hole through the center of the hexagonal body. Then a tap, a rotating cutting tool with external threads, is inserted into the hole. As it advances, the cutting edges of the tap shave material from the hole wall, forming a precise internal thread profile. During the tapping operation, cutting fluid is continuously supplied to cool the cutting edges, lubricate contact surfaces, and flush away metal chips. Once threading is complete, both bolts and nuts move on to final quality control. First up are geometric checks: diameter, thread pitch, thread depth, concentricity, and sharpness of the thread profile. Threads must match standard thread gauges perfectly. Even the tiniest deviation means rejection. Next come mechanical tests, including surface hardness, tensile strength, and torque resistance. Only after passing all these tests do bolts and nuts move to packaging. At this stage, the products are no longer semi-finished parts. They're full-fledged structural components, ready to ship to construction sites, power plants, steel bridges, or drilling rigs, where every bolt and nut will be responsible for holding together massive industrial systems. From raw steel rods through cutting blanks, heating, forging, thread cutting, inspection, and packaging, giant bolts and nuts complete a manufacturing journey that's precise down to the tiniest details. If you find this journey fascinating, hit that like button to support the video, drop a comment to share your thoughts, and subscribe to the channel to keep exploring the production lines that quietly keep our modern world running.
Hey everyone, on this channel we go behind the scenes where cameras usually aren't allowed. If you're into this kind of breakdown, hit subscribe and tap that bell so you don't miss new episodes. Every year, the world recycles over 1.5 billion tons of scrap metal, and hidden within this chaos of rust and mangled iron is something way more valuable than it looks. What seems like trash today could save your life tomorrow at 75 miles per hour. But how exactly does this pile of metal transform into a precision-engineered component trusted by millions of drivers? And why can even a tiny 1% error destroy an entire batch? There's one detail in this process almost nobody talks about, and it's what determines whether your car stops when it really matters. Today, we're breaking down the entire production of brake rotors, from the furnace to final inspection. It all starts with what most people would just call a junkyard. And that's pretty ironic. What will later stop your car at 75 miles per hour right now looks like a giant pile of rusty junk. Old cast iron radiators, car body fragments, twisted beams, and other metal scrap. It's all stacked in heaps on the lot outside the plant, and rain sends rusty orange streaks running down into the asphalt. But to this factory, it's all treasure. A massive electromagnet hanging from a crane scoops up several tons of this iron and drops it with a crash into the throat of a giant induction furnace. Induction, meaning the metal doesn't melt from fire, but from an electromagnetic field that heats it from the inside out, evenly and fast. If you stand too close, it's kind of terrifying. The furnace hums at such a low frequency that you don't really hear the sound. You feel it deep in your chest, like your heart's trying to sync up with this heavy industrial rhythm. The temperature inside the furnace climbs to 2,700 degrees Fahrenheit. At that kind of heat, even the toughest steel turns into liquid, more like glowing, ridiculously dangerous soup than anything solid or dependable. When the furnace tilts to pour out the molten metal, everything around you floods with bright orange light that makes you want to squint. No artificial beauty here, just brutal physics and an insane amount of heat. Every batch of metal gets tested instantly. Lab techs in special suits grab a small sample, cool it down, and within seconds determine its chemical makeup using a spectrometer. The device breaks the sample down into elements and spits out precise percentages of each component. If the carbon or silicon content deviates from spec by even 1%, the entire massive batch gets sent back for remelting without hesitation. Mistakes aren't tolerated here, because the cost of that kind of error to the end user could be way too high. Next, they pour this liquid fire into molds. They use sand casting technology here. Sand seems like an unreliable material, but at this factory, they mix it with special resins and under enormous pressure, it becomes hard as concrete. The molds are made with jeweler-like precision. The internal relief copies every detail of the future disc, including cooling fins and mounting holes. Metal fills the cavities inside the sand mold, and it's at this exact moment that the rough blank of the future brake disc is born. It doesn't look anything like that shiny part we're used to seeing in auto parts stores yet. Instead, it's something big, heavy, and really dirty. After pouring, the discs need to cool naturally. It's a long process, sometimes taking several hours, and this is critically important. If you try to speed up the cooling, say by splashing water on it, the metal becomes too brittle. A disc like that could just shatter into pieces at the first hard stomp on the brake pedal somewhere out on the highway in the rain. When the blanks cool down to just warm instead of glowing red hot, they head to the machining shop. This is where robot territory begins. They work 24/7, no lunch breaks, no complaints about tough working conditions. Each disc gets grabbed by a manipulator arm that loads it into a CNC machine. Special cutting tools shave off excess metal as easily as if it weren't solid cast iron, but a stick of cold butter. Chips spiral out red hot and drop into a collection tray while a smooth, precisely calibrated surface emerges from under the cutter. At this stage, fanatical precision rules. A deviation of 0.8 of a millimeter means hopeless scrap. A disc like that never makes it to the warehouse, because it'll cause vibration that'll just destroy a car's suspension in a few months and force the driver to shell out a ton of cash for repairs. The machine finishes one disc in several minutes, and each one comes out identical to the last. Robots don't get tired and don't lose focus by end of shift. It's fascinating to watch as the perfect, almost mirror-like surface gradually emerges from a rough and ugly form. Then they drill ventilation holes and internal channels into the discs. This isn't done for visual style like some people think. It's a critically necessary cooling system, without which the discs simply wouldn't survive serious loads. During heavy braking, the disc can heat up to 1,300 degrees Fahrenheit. At that temperature, it glows dark cherry red. If this heat isn't removed in time, the metal starts losing its friction properties, and the brakes just disappear at exactly the wrong moment. So these holes and channels, they're the result of extensive engineering calculations, not some design decision for looks. Each channel has a precisely determined diameter and angle, calculated so airflow pulls heat away from the working surface as efficiently as possible. Once all the excess shavings are removed, each rotor gets sent to dynamic balancing. It's a lot like what they do to your wheels at the tire shop, but the precision here is tens of times higher. A special device spins the rotor up to enormous speed and uses sensors to detect the slightest weight imbalance. At these rotational speeds, any imbalance turns into noticeable vibration, and the machine picks it up with gram-level accuracy. If one side turns out to be heavier by even 3 or 4 grams, the machine automatically drills out a tiny, nearly invisible dimple in just the right spot on the face to even out the weight. After that, the rotor is perfectly balanced and ready to perform at any RPM without any extra noise or judder. It's at this stage that the difference is made, whether the driver will feel every imperfection through the pedal or whether braking will stay smooth and silent at any speed. I asked the chief engineer how many of these rotors they produce in a single full workday. He just smiled wearily and said they stopped counting them individually a long time ago. They track output in thousands of tons of finished product per month. Just think about that for a second. This facility supplies parts for nearly half the European automotive market, which means every other car you see on city streets is probably stopping with rotors made right here, in this loud, scorching hot plant. Before packaging, the rotors go through a protective coating process. They're either painted with a special heat-resistant paint or coated with a thin, anti-corrosion, zinc-based layer. The coating gets applied in a chamber, the rotor hangs from a conveyor, and automatic sprayers evenly cover it from all sides. This is done so they don't turn into a rusty chunk of metal during long-term warehouse storage or while crossing the ocean in a shipping container. Sure, after the first few miles of driving, this paint on the working surface will completely wear off under the massive friction from the brake pads, but the edges and internal parts will stay protected from road salt and grime. The final, and arguably most critical stage, is the quality control check. And we're not talking about some tired worker giving it a quick once-over at the end of their shift. They use ultrasonic scanners and X-ray machines. They're hunting for internal defects, air bubbles or micro cracks you couldn't spot even with a magnifying glass. Ultrasound sends a wave through the metal, and if there's a void inside, the signal bounces back distorted. The machine flags the problem zone instantly. Even if the disc looks flawless on the outside, but the X-ray reveals a cavity just 2 millimeters wide somewhere deep in the metal, it gets sent straight to the shredder. Nobody cuts corners on safety here, because everyone knows full well, this part directly determines whether the driver and passengers live or die.
There's something almost poetic about watching a massive steel plate, thick as your fist, transform into a perfect cylinder. What we're seeing here is one of Central Europe's finest engineering firms working with a steel plate 4 3/4 inches thick, nearly 10 feet wide, destined to... Every second, the world produces 28 million tons of stainless steel. And behind the shine of every spoon, every faucet, every surgical instrument stands one metal: chromium. But here's what's mind-blowing. Chromium melts at 3,375 degrees Fahrenheit, and in the electric arc furnaces that produce it, temperatures hit 5,000 degrees, hotter than the surface of the sun. A single furnace consumes 4,000 kilowatt-hours of electricity per ton of alloy. That's as much as the average apartment uses in 4 months. 80% of all chromium in the world goes into making stainless steel. But where does this metal come from? Why are 99% of the world's chromite reserves concentrated in just a handful of countries? And what happens in that hellish zone beneath the electrodes, where ore transforms into molten ferrochrome? Stick around. You'll discover how black rock gives birth to the metal that makes steel immortal. Picture a massive electric arc furnace as tall as a 3-story building. 3 carbon electrodes up to 6 feet across plunge into a churning mass of glowing ore, coke, and fluxes. Between the electrode tips and the furnace floor, electric arcs crack and snap. Temperatures in this zone hit 5,000 degrees Fahrenheit. That's hotter than the surface of the sun. The air above the furnace shimmers with heat. Clouds of smoke and gas blast out from beneath the half-closed roof. Inside, real alchemy unfolds. Chromium ore mixed with coke melts down, oxygen escapes as carbon monoxide, and molten ferrochrome, an alloy of chromium and iron, flows to the bottom. This is a submerged arc furnace, and this is where most of the world's ferrochrome is born. The process runs non-stop. Fresh batches of ore and coke pour in from the top, molten metal and slag tap out from the bottom. A single furnace like this can pack 25 to 45 megavolt amperes of power. This is a monstrous amount of energy. An entire power plant runs just to melt the ore. When enough molten ferrochrome accumulates in the furnace, workers punch open the tap hole, a special opening in the furnace's side. And then the mesmerizing spectacle begins. A stream of white-hot metal and slag bursts out, flowing down a channel into an enormous ladle. The stream's temperature around 3,000 degrees Fahrenheit. The metal glows bright orange, almost white. The heat radiating from it is so intense that workers stand dozens of yards away, protected by special screens and fireproof clothing. Slag floats to the top and is drained off separately. The ferrochrome cools in massive molds, transforming into solid ingots weighing hundreds of pounds. These ingots are later crushed into pieces of the right size for sale to steel mills. But the process of obtaining ferrochrome, that's only the middle of the journey. It all begins with ore, mined deep in the earth. Chromite, the only industrial ore of chromium. It's a dark brown, almost black mineral with a metallic luster. The chemical formula? Iron and chromium oxide. Pure chromite contains 68% chromium oxide and 32% iron oxide. But in nature, perfect ores like that barely exist. Real deposits contain anywhere from 40 to 50% chromium oxide. Chromite forms in igneous rocks, in massive molten masses rising up from the Earth's mantle. The largest deposits are found in South Africa, Kazakhstan, India, and Turkey. These 4 countries account for roughly 80% of global production. South Africa is the absolute leader. Its deposits in the Bushveld complex contain 200 million tons of chromite. We're talking ore seams stretching for hundreds of miles and plunging thousands of feet deep. Kazakhstan holds reserves of 230 million tons. India? 54 million tons. Now the story. French chemist Louis-Nicolas Vauquelin discovered chromium in 1797. He isolated it from croquat, a bright red lead chromate mineral. The mineral's vivid color inspired Vauquelin to name the metal after the Greek word chromos, color. Because chromium compounds produce stunning colors, greens, yellows, oranges, reds. A year later, in 1798, Vauquelin isolated pure chromium by reducing the oxide with carbon. Iron with added chromium was first produced in the mid-1800s, and the first use of chromium as an alloying element in steel production happened in France in the 1860s. The revolution came in 1893 when Henri Moissan smelted chromium ore with carbon in an electric furnace and produced ferrochrome. This became the foundation of the modern industrial method, which has evolved but at its core remained the same. Chromite gets mined both through open-pit operations and underground mines. Open-pit mining gets used when the ore sits close to the surface. Giant excavators strip away the soil and overburden, exposing the chromite layers. Then they blast the ore, load it into haul trucks with capacities up to 300 tons, and transport it to the processing plant. Underground mining gets deployed for deep deposits. Tunnels get driven hundreds of feet down, sometimes miles. They blast the ore, load it into mine cars, and haul it to the surface. The extracted ore? It's not pure chromite yet. It comes mixed with waste rock and other minerals. That's why the ore needs processing. First, they crush it in massive jaw crushers. Chunks the size of a car get reduced to fist-sized pieces. Then they grind it in ball mills down to the size of sand or even dust. After that comes separation, isolating the chromite from the waste rock. The main method for enriching chromite is gravity separation. Chromite is heavier than waste rock. Its density is 4.5 to 4.8 grams per cubic centimeter, while the rock is 2 to 3 grams. The crushed ore is mixed with water, creating a slurry. The slurry passes through jig machines, concentrating tables, spiral classifiers, centrifugal separators. Under the force of gravity, the heavier chromite grains settle faster, while the lighter waste rock is carried away by the water flow. Magnetic separation is also used. Chromite is weakly magnetic, but modern high-intensity magnetic separators can attract it and separate it from non-magnetic impurities. After enrichment, they obtain chromite concentrate containing 46% or more chromium oxide. This is ready-made raw material for metallurgy. The concentrate is dewatered, dried, and sent to ferroalloy plants. Lump ore is needed for ferrochrome production. Fine powder doesn't melt well in the furnace. So the fine particles get agglomerated, sintered into large chunks. They mix the concentrate with fluxes and coke breeze, moisten it, and form pellets. Then they heat it to about 2,200 degrees Fahrenheit. The pellets sinter into solid lumps a couple inches across. Now the ore is ready for smelting. At the ferroalloy plant, chromite concentrate gets mixed with coke and fluxes in specific proportions. Coke is the carbon source that'll reduce the oxides down to metal. Fluxes, quartzite, dolomite, limestone, are needed to form slag with the right composition and melting point. The charge, the mix of ore, coke, and fluxes, gets loaded into the electric arc furnace from the top through special hoppers. Loading happens continuously or in batches depending on the furnace type. The electrodes, massive carbon cylinders, are submerged in the charge layer. When they switch on the current, an electric arc forms between the electrodes and the material beneath them. Temperature in the arc zone? 5,000 degrees Fahrenheit and higher. That's enough to melt any ore. Inside the furnace, complex chemical reactions take place. Carbon from the coke combines with oxygen from chromium and iron oxides, forming carbon monoxide that rises upward. Chromium and iron are reduced to their metallic state and fuse together, forming ferrochrome. Some of the carbon dissolves into the metal, producing high-carbon ferrochrome with a carbon content of 4 to 8%. Typical South African ferrochrome contains 52 to 54% chromium, 6 to 7% carbon, and 2 to 4% silicon. Ores from Zimbabwe with a higher chromium to iron ratio yield a product with 63 to 67% chromium. The molten ferrochrome and slag accumulate in the lower part of the furnace, the hearth. When enough metal has built up, they open the tap hole. Metal and slag flow into a ladle. The slag floats to the top and is poured off or skimmed away. The metal is poured into molds or cooled in special forms. Once solidified, the massive ingots are broken down by hydraulic presses or hammers into pieces of the required size. Ferrochrome production is incredibly energy intensive. A single ton of high-carbon ferrochrome burns through 2,000 to 4,000 kilowatt-hours of electricity. That's why ferrochrome plants get built in countries with cheap power, often right next to hydroelectric dams. Chromium recovery from ore hits about 90% under good conditions. The remaining 10%, it goes into slag. Slag isn't just waste. Metal particles get extracted from it using mineral processing methods, and what's left goes into construction. Ferrochrome isn't the end product. It gets shipped to steel mills where it's added to molten steel for alloying. Chromium gives steel corrosion resistance, hardness, heat resistance. Stainless steel contains 10 to 20% chromium. Average, 18%. It's chromium that forms a thin, invisible oxide film on the steel's surface, protecting the metal from rust. And so, having traveled from black rock in the Earth's depths through quarry explosions, crushing and processing, through the inferno of an electric arc furnace at 5,000 degrees Fahrenheit, ferrochrome is born. An alloy that gives steel eternal life and shine, resistant to time and corrosion.
Take up a stone. Bright red, heavy, looking like dried blood. It doesn't smell, doesn't burn, doesn't radiate. Just a beautiful mineral. Now throw it into a furnace at 1,300 degrees Fahrenheit, and liquid metal flows out. Silvery, heavy, cold to the touch. The only metal on Earth that stays liquid at room temperature. Mercury. A substance that has mesmerized alchemists for millennia, poisoned kings, and powered industry. And it's extracted from a stone that looks like a gemstone, but is actually just ordinary sulfide. Today, we're at a mine and processing plant where red rock turns into liquid silver. If you're into deep dives like this, subscribe and hit the bell so you don't miss new episodes. This red rock is called cinnabar, mercury sulfide, one of the few natural compounds where mercury shows up in Earth's crust. The chemical formula is simple: one mercury atom, one sulfur atom. Basically, nature locked liquid metal inside a sulfur cage, and to get it out, you've got to break that cage with heat. If you crack a chunk of cinnabar, the fracture surface reveals crystals with a diamond-like shine. The beauty's deceptive because the powder from this mineral is poisonous. Cinnabar was known even in ancient times. Egyptians used it as pigment, Romans painted palace walls with it, and Chinese alchemists believed the red ore was the key to immortality. Deposits are scattered across the planet, but the main ones are in Spain, Slovenia, China, and Kyrgyzstan. The Spanish mine at Almaden operated for nearly 2,000 years and gave the world more than a third of all mercury ever extracted. The ore sits in volcanic activity zones because mercury rises with hot solutions from deep within Earth's crust and settles in rock fractures as bright red veins. Sometimes cinnabar is so rich that the rock looks like someone painted it with scarlet dye. Mining starts underground. Miners drill into the rock with pneumatic jackhammers, place charges, and blast, bringing the whole face down. They load the ore into mine cars and haul it to the surface. It's hard, dangerous work. Even down in the mine, mercury vapor seeps from the rock, so ventilation runs at full blast. Mercury content in the ore is usually low, 1 to 12%. The rest is waste rock, sandstone, clay, quartz. But even 1% is worth going after because mercury fetches a high price. At the surface, the ore gets crushed in jaw crushers. 2 steel jaws squeeze the rock, breaking it down to gravel size. Then, vibrating screens sort the pieces by size. The fines go straight to the furnace. Oversized chunks loop back for another round of crushing. Dust is a whole other problem. It carries mercury, and breathing it is dangerous. So the crushing plant runs heavy exhaust and wet dust suppression. Workers wear respirators, and at the entrance, there's a mercury vapor monitor. If the needle swings into the red, they shut down the plant and air it out. Now comes the most critical step, roasting. The principle is simple yet brilliant. Heat cinnabar to 1100 to 1300 degrees Fahrenheit in air, and the sulfur bonds with oxygen and escapes as sulfur dioxide gas, while the mercury vaporizes. 2 substances locked in stone for millions of years part ways forever. One into the air, the other into a pipe. Roasting furnaces come in different designs, but the classic is a rotary kiln. Picture a massive steel drum, 60 to 100 feet long, set at a slight angle. Ore gets fed in from the upper end, burners fire from the lower. The heat inside is so intense, the furnace walls glow a dull cherry red. The kiln rotates slowly, tumbling the ore, gradually pushing it downward as it heats up more and more. When the temperature hits the sweet spot, the cinnabar breaks down. Sulfur burns with a bluish flame, and mercury vapor, invisible and deadly, rises and travels with the flue gases into the condensation system. The spent rock, now stripped of mercury, spills out the lower end of the furnace into a waste pile, gray, lifeless, having surrendered everything valuable to the fire. Condensation is the moment when invisible vapor transforms into that actual liquid metal. Gases from the furnace pass through a long system of pipes and chambers that gradually cool down, usually with water fed through jackets on the outside. Mercury condenses first. Its boiling point is only 675 degrees Fahrenheit, so when the gases cool below that mark, silvery droplets start settling on the condenser walls. They trickle downward and collect in receivers, steel or ceramic containers. The sight is mesmerizing. From the pipe, as if from nowhere, heavy silvery liquid drips down, falling into the collector with a distinctive, soft sound. Not a clang, not a thud, but something in between. Because mercury is viscous and heavy, 13.5 times heavier than water. A quart of mercury weighs more than 28 pounds. Try picturing a quart of milk that weighs as much as a bucket of cement. The raw mercury from the condenser isn't ready for sale yet. It's swimming with impurities. Soot particles, water droplets, traces of other metals. It's cleaned in several stages. First, they filter it through chamois leather or special fabric. Mercury passes through the pores while the dirt stays behind. Then, they wash it with diluted nitric acid, which dissolves impurities like zinc, lead, and tin, leaving the mercury itself untouched. The final purification is vacuum distillation. Mercury gets heated in a vacuum, where it evaporates at a lower temperature, while impurities with higher boiling points remain at the bottom. They collect the condensate, and now you've got mercury at 99.9% purity. It's poured into standard steel flasks holding 76 pounds. That's the international standard called a flask. The container's small, about the size of a thermos, but lifting it one-handed? Not easy. All because of that incredible density. Safety at a mercury plant is a world unto itself. Mercury vapor has no color and no smell, but it's extremely toxic. Just a few hours of breathing it can give you serious poisoning. Chronic exposure destroys the nervous system. That's why hatters in the 19th century went mad. They used mercury to treat felt and inhaled the fumes for years, hence the phrase, mad as a hatter. In a modern plant, the entire facility operates under negative pressure. Air is constantly pulled inward, not pushed outward, so vapors don't escape into the atmosphere. Floors are coated with a special non-porous covering. If mercury spills, the droplets won't roll into cracks, but stay on the surface where they can be collected with a specialized vacuum or a sulfur trap. Sulfur powder binds mercury into harmless sulfide. Every worker carries a personal dosimeter that measures accumulated vapor exposure per shift. Exceed the limit, and you're pulled off the floor until your levels normalize. Where does all this mercury go? Historically, the biggest consumer was gold mining. Mercury dissolves gold, forming an amalgam. You then heat it up, and the gold evaporates out. Conquistadors in South America use this method, and it's exactly why the Spanish crown exploited almaden for centuries. Today, amalgamation is officially banned in most countries because of the catastrophic environmental damage. But in artisanal mining across Africa and Southeast Asia, millions of prospectors still use it. Poisoning rivers, poisoning soil. Other applications: chlor-alkali industry, thermometers, barometers, mercury lamps, electrical switches, catalysts. But the world is slowly moving away from mercury. In 2013, the Minamata Convention was signed, named after a Japanese city where, in the 1950s, thousands of people suffered devastating poisoning. Mercury leaked into the bay from a chemical plant. It built up in fish. And the people who ate that fish started losing their sight, their hearing, their coordination. The Minamata tragedy became a symbol of mercury pollution for decades to come. Mercury production worldwide is plummeting. Back in the mid-20th century, mines pulled out up to 10,000 tons a year. Now, less than 2,000. Most mines have shut down. The famous Almadine in Spain stopped operations and turned into a museum. These days, mercury increasingly comes from recycling, old thermometers, lamps, industrial waste. But humanity can't completely abandon it yet. Some chemical and electrochemical processes simply have no substitute. When you stand next to a flask where this heavy, silvery liquid sloshes around, it's hard to believe that an hour ago it was part of a red rock that sat underground for millions of years. Cinnabar guarded mercury like a safe guards valuables, and only fire could pick that lock. An ancient process, simple at its core, dangerous in execution, and still without an alternative. Every year, the world mines thousands of tons of metals, but only one is so dangerous it can kill you even as dust, and yet helps us peer 13 billion years into the universe's past. That's beryllium, a metal lighter than aluminum but many times harder than steel, a metal without which the James Webb Space Telescope wouldn't exist. But there's one detail almost nobody talks about. Why does producing it feel like a chemical nightmare? And why does working with it become a deadly gamble? And what exactly are those factories hiding behind thick, protective glass? Subscribe so you don't miss out. You'll learn something that'll forever change how you think about metal. Let's jump straight to the numbers because they're absolutely mind-blowing. Look at this block of metal. Appears to be just another gray hunk of iron, but try to lift it and you'll nearly clock yourself in the chin from the surprise. Beryllium has a density of just 1.85 grams per cubic centimeter. That's almost 30% less than aluminum, which we've always considered the gold standard for lightness. But here's the kicker. Despite being this lightweight, beryllium is 4 times stiffer than steel. Its elastic modulus hits an incredible 303 gigapascals. What that means is this material puts up insane resistance to any deformation. You could build a structure thin as paper, and it would still hold its shape under colossal stress. On top of that, Beryllium has this exceptional ability to maintain its strength at high temperatures, making it absolutely irreplaceable in the aerospace industry. The extraction process, that's a whole chapter in the textbook of industrial survival. The primary source here is a mineral called bertrandite, mined in the deserts of Utah. The ore contains just 0.5% beryllium. To extract this metal, the rock gets crushed and dunked into sulfuric acid, turning everything into a chemical slurry. Then, through a series of complex manipulations with hydroxides and fluorides, they get pure beryllium fluoride. They mix it with magnesium in massive crucibles and heat it up to 2400 degrees Fahrenheit. The magnesium grabs the fluorine, and shiny metallic grains settle to the bottom, so-called pellets, or beryllium pebbles. Each grain is only a few millimeters across, but it's from these tiny pieces that parts for spacecraft and military hardware will eventually be assembled. But this is just the beginning, because working with them directly is impossible. And here's where we get to the most dangerous part of the tour. Beryllium is a genuine toxic bomb. Its dust causes chronic beryllium disease, which basically makes your lungs shut down. All it takes is breathing in a microscopic amount of particles, and your immune system starts attacking your own tissues. The disease can show up years after exposure, when you've long forgotten that one day you spent at the facility. So nobody here pours the metal into molds like cast iron. Instead, they use powder metallurgy methods. Metal grains get ground into fine powder in special mills under vacuum. Every single dust particle has to be controlled. Then, they pour this powder into massive steel capsules and subject it to vacuum hot pressing. Imagine hundreds of atmospheres of pressure and temperatures over 1800 degrees Fahrenheit, simultaneously crushing this powder, forcing it to become a solid block. This goes on for hours until the structure becomes perfectly uniform. Why did the telescope engineers choose this hellish material for their mirrors? It's all about the cold of space. James Webb operates at Lagrange Point 2, about 930,000 miles from Earth, where temperatures plunge to minus 370 degrees Fahrenheit. Regular glass deforms unpredictably when it cools this much, expanding in one spot, contracting in another. But beryllium has a unique property. Its thermal expansion coefficient at low temperatures becomes virtually zero. It basically freezes in place. The shape stays constant no matter how brutal the cold gets. This made it possible to build mirrors that remain perfectly smooth even in the savage cold of deep space. Each of the 18 mirror segments measures 4.3 feet across but weighs just 44 pounds. If they were made from glass, each one would tip the scales at over 200 pounds, and the rocket simply couldn't lift off the ground. Each mirror was carved from a single block, removing 90% of the mass from the back to create a lightweight honeycomb structure. This is called lightweighting. The walls there are just a few millimeters thick. After that, polishing begins. It's done using computer systems that remove irregularities measured in nanometers. 1/1000th of a meter. That's the precision we're talking about here. If Webb's mirror were the size of the Atlantic Ocean, the biggest bump on its surface wouldn't be taller than a regular coin. Then the mirrors are taken to a cryogenic chamber, where they're cooled to space temperatures, microscopic warping is measured, and then they're polished again to compensate for those changes. This cycle was repeated dozens of times over several years. Now take a look at this color. We're used to seeing telescope mirrors in gold, but underneath that gold lies pure beryllium. The gold is only applied at the very end through vacuum deposition. The gold layer is just 100 nanometers thick. That's 1,000 times thinner than a human hair. The entire massive mirror, covering about 270 square feet, used only about 1.7 ounces of gold. That's like 3 or 4 wedding rings rolled out across a giant surface. Gold is essential because the telescope searches for infrared radiation from the very first stars that ignited 13.5 billion years ago. Beryllium provides rigidity and stability, while gold delivers perfect reflection in the precise wavelength range needed. At this facility, safety protocols look like paranoia, but it's justified paranoia. See those yellow lines on the floor? You can't cross them without special footwear. The air in the shop completely refreshes every 3 minutes. Beryllium levels in the air must not exceed 0.2 of a microgram per cubic meter. That's so small you couldn't even see it under a microscope. But sensors are everywhere. After every shift, each worker goes through a special shower, and their clothing gets disposed of as hazardous waste. That's the price we pay for the ability to peer into the depths of space. But beryllium isn't just about space. Look at these tiny components for aircraft engines. Because beryllium conducts heat better than most metals, it's perfect for parts that need to cool down fast. Its thermal conductivity is around 210 watts per meter Kelvin. It pulls heat away faster than aluminum and doesn't melt until 1287 degrees. This lets planes fly faster and engines run more efficiently. Here's another wild fact you probably won't hear in chemistry class. Beryllium is almost transparent to X-rays. Take an X-ray through a steel plate, you'll see nothing. But with beryllium, the rays pass through like it's not even there. That's exactly why the windows in every X-ray machine and CT scanner at hospitals are made from beryllium foil. It lets doctors get crystal clear images of your body without losing radiation power at the machine itself. So what does all this cost? If you want to buy a kilogram of pure beryllium, expect to shell out anywhere from $800 to $1,000. But that's just raw material. The cost of a finished part can be 10 times higher or more because of how difficult it is to machine and all the safety precautions required. A single web mirror segment costs millions of dollars when you factor in all the years of testing and polishing. And even with these insane prices, global beryllium production doesn't exceed a few hundred tons per year. That's how rare and difficult it is to work with. Thanks for watching. Hit that like button if you love real science as much as I do. See you at the next classified facility.
Every year, the world produces over 4 million tons of hollow structural sections, and that's just in the US. Picture this, that's enough to build 400 Eiffel Towers annually. But behind these massive numbers lies the silence of steel giants we never see, because they're hidden inside buildings, bridges, and machines. How does rusty scrap metal transform into tubes capable of supporting the weight of entire bridges and weathering the storms of time? And what secret makes them both lightweight and incredibly strong? Stick around till the end, and you'll discover a secret you never knew existed. The market for hollow structural sections, where our heavy wall tubing reigns supreme, is a massive chunk of America's steel industry. Every year, the country cranks out over 4 million tons of these tubes. That number is mind-blowing. To put it in perspective, the entire Eiffel Tower weighs about 10,000 tons of steel. That means in a single year, American mills produce enough square and rectangular tubing to build 400 Eiffel Towers. It's an entire forest of steel giants sprouting up annually. We just don't see it because it's hidden inside structures. Mountains of scrap metal, remnants of cars, construction frames, old machinery sit waiting for their fiery rebirth. A giant crane with an electromagnet scoops up this metallic chunk and feeds it into an electric arc furnace.
Down there, in that roaring inferno where temperatures hit nearly 3,000 degrees Fahrenheit, this scrap metal transforms into a boiling, blinding lake of molten steel. Into this melt, like a chef adding spices, they introduce alloying elements, so the future pipe isn't just strong, it can withstand extreme loads and won't crack in freezing cold. Then this river of fire flows into a continuous casting machine, where it cools and solidifies, becoming long, massive steel billets. For our future pipe, these are typically thick, round slugs called blooms. Automatic cutters slice off pieces to the required length, and these hot but now solid cylinders are ready for the really interesting part. This is our blank, our solid chunk of metallic dough. But how do you make a hole in it when it's hard as rock?
To do this, it's sent to a heating furnace, where its temperature is brought back up to that perfect plastic state, 2,300 degrees Fahrenheit. And from there, glowing white hot with a blinding yellow radiance, it moves to the piercing mill. This is the heart of the entire process, and it's real industrial magic. Picture two massive barrel-like rolls spinning in the same direction. They're set at an angle to each other. The hot steel cylinder enters between them, and here's where something incredible happens. As they spin, the rolls don't just forcefully push the cylinder forward, they also make it rotate at a crazy speed. Because of this rotation and compression, enormous stresses build up right at the center of the metal cylinder, and the metal there literally loosens up, preparing to split. And at that exact moment, from the other side, a special piercing rod, or mandrel, is fed in to meet it. It plunges into that loosened center like a knife through butter, literally punching straight through the solid billet, transforming it into a thick-walled tube. It's an incredible sight. A solid chunk of metal becomes hollow in mere seconds, all happening with a roar and grinding that shakes the ground. The piercing process was invented in the late 19th century by the Mannesmann brothers in Germany and remains the primary method for producing seamless tubes to this day. But now we've got a round tube, and we need a square one. Our hot, freshly pierced tube immediately moves to the next stage, the forming mill. This is a series of roller pairs, but these ones aren't round. They have special grooves whose shape gradually transitions from round to square. The tube flies into the first pair of rollers, which squeeze it slightly from the sides.
Then it rotates 90 degrees and enters the next pair, which squeezes it from different sides. And so, step by step, passing through several of these gates, our round tube transforms right before your eyes into a perfectly square one. It's like a skilled sculptor, gradually, blow by blow, giving stone its desired shape. The final finishing rolls calibrate the tube with incredible precision, guaranteeing that all its walls have uniform thickness and all corners are perfectly square. The standard sizes are impressive. There are tubes with cross-sections of 500 by 500 millimeters. That's about 20 inches wide, and the wall thickness on these monsters can easily exceed 25 millimeters. Picture a steel wall as thick as a big encyclopedia. The weight of such a tube is simply colossal.
A single yard of this pipe can weigh over 800 pounds. That's like having 4 grown men standing on every yard of its length. And a standard 40-foot section, that'll clock in at over 10,000 pounds, the weight of 2 full-size SUVs, like a Range Rover. And that's just one piece. But here's the thing. Their real genius isn't the weight itself, but how intelligently it's distributed. That's their superpower. Picture a solid steel bar and a hollow pipe of the same weight. The pipe will be way more resistant to bending and twisting. Why? Because all the material sits on the outside, as far from the center as possible, and that's exactly where the greatest stresses hit under load. The hollow core? It just saves weight. Same principle as bird bones, hollow but incredibly strong.
That's why hollow profiles have the highest strength-to-weight ratio of any structural steel shape. This makes them the perfect choice when you need maximum rigidity without extra tons, in crane booms, heavy equipment frames, bridge trusses, and even roller coaster structures. It's because of these tubes that modern skyscrapers can withstand hurricane-force winds, and bridge structures last for decades, carrying millions of tons of cargo. From the final roller, a long, red-hot, now square tube emerges. It travels along a roller conveyor to a cooling table, where it slowly cools down, gaining its final, rock-solid strength. During cooling, the metal can warp slightly, so each tube is run through a straightening machine, a system of rollers that straightens it to perfectly linear precision.
Now we've got a perfect, strong, but really long pipe. Time for the final operations. A massive saw roars to life and cuts it into standard lengths, say 20 or 40 feet. Each section goes through strict quality control. Specialists check its geometry, wall thickness, angle precision. Then they X-ray it with ultrasound to make sure there aren't any hidden internal defects. Modern flaw detectors can spot micro cracks smaller than a millimeter, invisible to the naked eye. Only then does the pipe get marked with all its info: steel grade, dimensions, batch number, production date. The finished, inspected pipes get bundled by robotic cranes, strapped down with heavy steel bands, and shipped off to the warehouse. And just like that, traveling from rusty scrap metal through the fiery heart of the furnace, surviving brutal piercing and precise forming, this humble yet incredibly strong steel rectangle emerges, ready to become the silent but reliable backbone for humanity's most ambitious creations. From the skyscrapers of Dubai to the bridges of San Francisco, from oil rigs in the North Sea to the frameworks of space launch pads, everywhere these unsung heroes of modern civilization are hard at work. They don't demand applause, they don't seek recognition, but it's on their steel shoulders that our world stands. And now you know their story. From fire to structure, from the chaos of scrap metal to the mathematical precision of engineering calculations. This is the real magic of industry.
It's 1,250 feet long, 223 feet wide, and from keel to top deck, it stands 112 feet tall, like a 12-story building. This is a supertanker, the largest moving object ever built by human hands. It displaces 440,000 tons. Its holds can carry 3 million barrels of oil, enough to fill up 2 million cars. It won't fit through the Panama Canal, can't pass through Suez fully loaded, and to dock one, ports have to build dedicated offshore terminals. One of these ships cost $130 million, takes 2 years to build, and today, you're going to see how a steel giant capable of hauling an entire sea of oil across the ocean comes to life. Everything starts with a design. The engineering team works on blueprints for 18 months, around 50,000 separate parts, over 125 miles of welded seams. Hundreds of engineers calculate every ton of metal, every degree of hull curvature. A supertanker's hull isn't one solid structure. It's about 200 massive sections, welded individually, then assembled into a single unit. Each section weighs between 300 and 600 tons. When the design's ready, it goes to steel mills. One tanker needs 45,000 tons of specialized marine-grade steel. That's 6 times more than the Eiffel Tower. Steel arrives as sheets between half an inch and an inch thick. Each sheet runs 40 feet long, 10 feet wide, weighing up to 10 tons. Just hauling the steel takes several thousand rail cars. The finished steel storage yard at the shipyard covers 20 football fields. Tanker steel is special. It's a shipbuilding alloy with reduced carbon content and manganese additives. It withstands impact loads at low temperatures and won't crack during storms in northern seas, where water can hit 28 degrees Fahrenheit. Next up, cutting. Steel sheets enter the gas and plasma cutting shop. Plasma torches slice through metal with precision down to 0.04 inches. Arc temperature? 36,000 degrees Fahrenheit. That's 3 times hotter than the surface of the sun. A single sheet, 1 inch thick, gets cut in 2 minutes. But there are tens of thousands of sheets. The shop runs 24/7, 3 shifts, no days off. From these sheets come the future structural elements: frames, stringers, bulkheads, plating. Every part gets marked, numbered, and sent to the next stage. Then, bending. Massive rollers and presses give the steel sheets their required curves. Bow plating, rounded sides, stern contours. A 2,000-ton press bends steel like paper. Bend radius? Up to 12 inches per 3 feet of length. Now comes the most critical phase, assembling the sections. Each section is built on a separate assembly pad inside the facility. Think of them as mini factories within this massive plant. Workers lay hull plates onto the jig matrix. Steel frames, the ship's ribs, get welded on. Spacing between frames? Exactly 29.5 inches. Not more, not less. Off by half an inch, and the hull could crack in a storm. Welding is automated and semi-automated. Up to 40 welders work on a single section simultaneously. Weld depth runs 0.3 to 0.4 inches. Every seam gets checked. X-ray, ultrasound, and dye penetrant testing. One section takes 3 weeks to complete. During that time, they lay down 5 tons of weld metal. After assembly, an 800-ton gantry crane hoists the section and transfers it to the slipway. Before mounting on the slipway, each section undergoes geometric inspection. Laser systems measure it at thousands of points. If even one point deviates from the blueprint by more than 1/8 of an inch, the section goes back for rework. Because if one section's crooked, the next 20 won't fit into place. The slipway is a massive dry dock, 1,476 feet long, 295 feet wide, 49 feet deep. This is where the entire hull comes together. Assembly starts with the keel, the central longitudinal beam running the full length of the ship. It's the tanker's backbone. Everything depends on how precisely it's positioned. The keel is aligned using laser levels with accuracy down to 0.08 inches, over 1,312 feet. Then the first bottom section gets mounted onto the keel. Cranes fly it in overhead. 4 riggers guide the 500-ton mass into position with inch-perfect precision. Sections are joined by welding. Each seam runs dozens of feet. Welders work inside compartments, outside on scaffolding, overhead on suspended platforms, sometimes 200 people simultaneously on a single hull. If you're fascinated by how humanity builds machines that challenge the ocean itself, subscribe to the channel. There are many more processes ahead that'll blow your mind with their scale. While the hull is being assembled, the engine room is installed simultaneously. This is the heart of the supertanker. The main engine is a diesel standing 46 feet tall, 89 feet long, weighing 2,300 tons. It's the largest reciprocating engine in the world. Each cylinder is 38 inches in diameter. The piston stroke, over 8 feet. 14 cylinders total. The engine produces 108,000 horsepower, enough to power a city of 50,000 people. It runs on heavy fuel oil and burns through 250 tons of fuel per day at full throttle. It's installed through the upper deck while it's still open. A crane lowers the engine into the engine room in sections. Then specialists assemble it on site. Assembly and calibration of a single engine take 4 months.